AI agents. It's all anyone can talk about in the AI space at the moment. But what are agents exactly? And how hard is it to build one for yourself? In this tutorial, we're going to explore how to build our very own AI agent from scratch that can actually help us to learn a new language. We're going to be using cutting-edge tools like LangGraph and MCP in order to help our agent create language learning flashcards. And we're also going to be exploring different types of LLMs, from proprietary models to open source, and also specialized reasoning models to more general purpose models that can help us with translation. We're going to cover cleaning and preparing text data using some classic natural language processing techniques, the basics of React agents in LangGraph, switching your agent from using a paid proprietary model to using a free local open source one, adding additional custom tools, creating a tool that uses a translation LLM to translate our word list, and then finally, connecting the agent to an MCP server and letting it use its tools in order to create language learning flashcards. We'll round off this tutorial by discussing some important security considerations that come when building agents, and things we can do to limit the risk that our agents leak sensitive data or expose our system to malicious actors. Before introducing any new concepts, I will cover a little bit of theory so you can understand what's going on, but largely it's going to be a very hands-on, code-driven tutorial that's going to allow you to have your very own language learning agent by the end. And in order to get the most out of this tutorial, I would recommend it for people who have solid experience in Python and some understanding of machine learning, but you don't need to have a background in deep learning or natural language processing in order to complete this material. Finally, I hope you'll be able to see by the end of this tutorial that what we cover has a lot of different applications for working with text data and large language models. Now, of course, we're going to be thoroughly covering the basic building blocks of building a LangChain agent. So you'll be able to go away and create your own agents, of course, but we're also going to learn some important principles about text cleaning and processing and machine translation, which you can also use to apply to other projects. So before we get started, I also just want to take a moment to introduce myself. My name is Jodie Birchall, and I've been working as a data scientist for around 10 years now, particularly in the area of natural language processing. Prior to that, I completed my PhD, and I spent a couple of years in academia. I'm currently working at a company called JetBrains, which is well known for its development tools. And in this tutorial, we're going to be spending a lot of time with one of those tools, a Python IDE called PyCharm. And I'm going to be showing you some really great features that PyCharm has to help us with data science projects and also with building agentic applications. If you'd like to reach out to me about this tutorial or any other topic, my social media links are in the description of this video, along with some other content that I've created that you might find interesting. And if you like this video, we really hope that you'll consider liking it and subscribing to this channel. So with all of that covered, let's get started. So let's first talk about the tooling that we're going to use in order to complete this tutorial. And we're going to be doing everything in an IDE called PyCharm. Now, PyCharm is an IDE that's designed specifically for working with Python. So it has a lot of cool functions that make building and debugging agents a lot easier, and also for working with the data that's going to be underlying our agent. So if you don't already have a copy of PyCharm, you can download it by going to jetbrains.com/PyCharm. And if you go to the download button, that's going to take you to a page where you can download your OS specific version and also give you a free 30-day trial, which is going to give you access to all the pro features that we're going to be using in this tutorial. Alternatively, you can download PyCharm through the JetBrains Toolbox app. This is really handy, especially if you're using multiple JetBrains IDEs, but it is also the easiest way of updating PyCharm. So we have 3 different releases that come out a year, and it's very, very easy to update those through Toolbox. And then finally in this tutorial, we're also going to be using some features from JetBrains AI Assistant. So this is basically JetBrains' coding assistant, and it gives some very, very helpful features for building and testing agents. So this is a separate subscription to PyCharm, but if you would like to also use this, go to jetbrains.com/AI and you can see the subscription plans there. So once you've downloaded PyCharm, you have two different ways of opening it depending on how you've installed it. You can either have it as an icon in the dock and just simply click on it to open it. Or if you've installed it via Toolbox, you can pop up, open the Toolbox app, and then open PyCharm directly from there. So when we open PyCharm, we land on this landing screen. And this gives us multiple ways of starting to work with Python. So we can either quickly create a new notebook or a new script. We can create a full new project. We can open an existing project, or we can clone a project from somewhere like GitHub. So because we're going to be building a whole application, we're going to select New Project. So this directs us to another screen, and on this screen we need to do two things. The first is that we need to name our project. So I'm going to call it Language Learning Agent, which is pretty logical. And the next thing we need to do is to pick our interpreter type. So we can see we've got three options here. We've got Project Virtual Environment, we've got Base Conda, and a Custom Environment. And what is very cool is that essentially PyCharm is directing you into best practices from the start. It's encouraging you to create a virtual environment so that all of your dependencies are isolated. And what's even better is I'm going to stick with Project Virtual Environment. If I click the drop-down menu below that, you can see that it's actually also detected all of the different installs of Python that I have on my machine. It's detected my pym install, it's detected my sort of system Python, which I've installed with Homebrew, and it's also detected UV. So this makes it so easy to set everything up. So I'm going to go ahead and use UV for this project. And with that, we're done. We just need to go ahead and create the project. So because this is a data science project, obviously the first thing we need is some data. So because this is a language learning app, I figured the most appropriate data set would be a list of all words in as many languages as you can get your hands on. And so I found this project on GitHub, which is trying to do just that. Basically, the author is trying to crowdsource different vocabulary lists in as many languages as possible. So I'm going to be sharing the link to this in the resources, but if you want to type it in manually, you can see the link right here. So if we have a look through the repo, we can see that indeed there are a huge number of different languages available in this project. So it certainly does look promising. But from the outset, we need to consider that this is a crowdsourced project. So in the coming steps, we're going to inspect the data and we're also going to clean it. And you're going to see that there are a number of potential problems with this data set and some limitations. So what I'm also hoping is that the techniques that I teach you in this tutorial are something that you can take away and apply to your own agent building projects. So you may want to have a look at other data sets that you can use for this project. So one place where you can get really great text data sets is Kaggle datasets. So basically, if you pop over to kaggle.com/datasets, you can get access to a whole bunch of really cool data sets that have been provided by the community or other sources. And if we click on the tag NLP, this gives us access to all of the text data sets. You can already see some pretty interesting data sets from the top ones that we can see. Things like a recipes data set, which is obviously something that could definitely be used for an agentic application. And then another classic source of datasets is the UC Irvine Machine Learning Repository. This is at archive.ics.uci.edu/datasets. And if we go to this website and we filter the datasets by data type, text, we can also get access to some really cool text datasets, which again, you could use as the basis of any machine learning project, including obviously an agent. But for now, we're going to be working with our All Words in All Languages dataset for our language learning agent. So the easiest way to get this data, because it's in GitHub, is just to clone it to our local machine. So the first step is obviously to copy the location of that repository. So let's now head back to PyCharm, and you can see that here we're in that project that we just created, and it's empty and it's ready for us to start building our agent. And around the sides, you may have seen a whole bunch of different icons. These represent different tool windows that come built into PyCharm. They give a lot of different functionality out of the box for working with Python, for working with data, and for working with agents, as you're going to see. So we're going to be exploring quite a lot of these tool windows as we go through the tutorial, but for now, we're going to start with the terminal. So let's now open the terminal tool window. And you can see that this creates a new terminal session for us, very conveniently within the IDE. And what's very nice is that it's already within our project directory, and it's already activated the virtual environment, so we don't need to do that. So let's go up one level of the directory. We'll exit our directory and go into the directory that it's contained with in order to clone our project. So we use the cd command to go up one level, and then we use git clone with the address of the repository that we just copied in order to clone it. Then what we want to do is copy the data over to our application. So the first thing that we're going to do is to go back into our project directory using the cd command, and then we're going to make a new directory for that data, which we'll call raw word lists. Okay, so now that we have this blank directory, we can now copy over all of the data. So basically we're going to use the cp command, and we will copy from the directory all words in all languages, which is obviously up one level out of our directory. And then we can use this nice notation with the curly braces in order to copy all of the directories at once. And then we specify that we want them copied into raw word lists. And then finally, I've actually noticed that in the original data, the directory for Ukrainian actually has a typo. So we can use the mv command in order to update the name from the misspelling of Ukrainian to the correct one. So now that we have our data, we can move on to the next step, and that is getting our project dependencies. And we can actually use another PyCharm tool window to help us with this, and this is the Python packages tool window. So if we open up this tool window and we search for Pandas, which we're going to be using to help with our data inspection and cleaning, we can see that if we click in the list for PyPI, this gives us the exact information about this package that's present on PyPI. We can also see that it's very, very easy to install different versions of Pandas. So you can either by default install the latest, or you can install a whole bunch of different releases of this package. And you can do this with every package through the Python packages tool window. So we've hit install, and while that's installing, which is very fast with UV, we're going to go ahead and install our next package, which is IPython widgets, which we need for running some things in Jupyter. The next two packages we're going to install are SpaCy and SpaCy transformers. So these are packages which are designed to allow you to do very, very powerful traditional natural language processing. And we're going to be using these in order to do some cleaning up of our data before we make available to the agent. So we'll be talking more about the SpaCy packages when we get to the inspecting and cleaning the data sections, but know that this is a very classic package for doing sort of more traditional natural language processing, as well as more cutting edge stuff. The next package is wordfreq. This is for looking up the frequencies of specific words. And we're also going to be using this as part of our data cleanup and processing. And then the last package that is not concerned directly with building our agent that we're going to install is python.m. This is a really nice way of securely managing your API keys in a way that means you don't have to copy and paste them directly into your script or into your Jupyter notebook. Okay, so let's now install the packages that we're going to need specifically for developing our agent. Now, the first of these is typing extensions, and this is for essentially managing specific fields that the agent needs while it's running. So you're going to see more about what I mean when we start building the agent, but for now, just know that we need this package. The next is LangChain Core. We're going to be largely using this package to help us distinguish between the types of messages that we send to the agent, either system messages, which are instruction sets, or human messages, which are user inputs. And the next package is, of course, LangGraph. This is going to be the backbone of our agent, and it contains many important components that we need that we're going to see in the next section of this video. This includes components for building our agent graph, for keeping track of the agent state, and connecting to LLMs. And don't worry if you don't know what any of these are right now. We are going to be going over everything step by step in the next section. So the next is LangChain OpenAI and LangChain Ollama. So these packages are going to allow us to use the LLMs that are going to be at the core of our agentic application. And as I mentioned in the introduction, we're going to be using both a proprietary model and comparing that with the use of an open source model. So we need both of these packages to be able to access those models. So finally, we need the package LangChain MCP adapters. And this is going to allow us to connect to the MCP server that we're going to be using to create our flashcards in the end. So with all this setup done, we are finally ready to start looking at our data. So to start, we're going to create a new Jupyter notebook because I prefer to always do my data exploration in Jupyter notebooks. So we just right click on the project name, we go to new and go to Jupyter notebook. And then we're going to be prompted to enter a name for that notebook. So we're going to call it Clean Wordless. And with that, we have a new notebook set up and ready to go. So to get started, we're going to import our dependencies. So we're going to be using CSV and OS to explore the raw word list that we have just copied over. We're going to be using Subprocess to download some additional models that we need. And we're going to be using the punctuation method from string in order to do some string cleaning. We're going to be using Pandas to basically manage the data in a data frame and explore it a bit more easily. And as I mentioned earlier, we're going to be using SpaCy transformers, and the Zipf frequency method from wordfreq in order to clean up the data and also add some additional information about it. So to get started with exploring our data, one of the most basic things we can check is how many words are in each of these word lists, because it's kind of known what the sort of general vocabulary of a language should be. So if we can have a look at the numbers of words, we can see whether they actually look right, whether there's too few or too many. So the first one we're going to open up is the English one, because I'm a native English speaker. It's the easiest one for me to check. And we're going to use the reader method from the CSV package in order to open those up and read how many elements there are in that. And what it's told us is the total number of elements is around 460,000. Now, this seems high. I know that a general sort of amount of words in English is not really in this ballpark. So this already tells us that we may have some cleaning to do because there's just too many words here. That seemed to work pretty well for English, so let's repeat that for all of the languages. So in order to make it easier to generalize this method, let's turn that code written specifically for English into a method that can be used for any of the languages. So let's turn it into a function called count CSV elements in file. We replace the specific file path for English with a file path argument, and then we have a nice general function we can use. So we're going to loop over each of the files that are in that raw word list directory. So the first thing I'm going to do is create blank lists to contain the languages that are extracted and also the total word counts. And then we use the walk method from the OS library to go through each of the files in that directory and essentially get the file name, split out the first element because that is the name of the language, and keep that as a string and append it to the languages list, and then apply that count CSV elements in file method to each of the language files and append that count to the total words list. And then we go ahead and run that. It's very quick. And then to make it a little bit easier to work with, what I'm going to do is to pass these two lists, the language list and the total words list, into a dictionary inside a Pandas data frame. And that means that essentially we are going to get this data frame, which contains two columns with the language and the total word counts. So we can already see that things may not be entirely okay with this data set. We can see that, say, the count for Macedonian looks very low, and the count for German looks really large. But in order to get a clearer overview of this, we can use a really nice feature built into PyCharm's Panda data frames, which is the chart view. So we just go ahead and we click the chart view button, and that automatically puts us in this view. Now we can see out the gate, we already have a bar chart, which is pretty much showing what we want. But in order to make it a little bit more intuitive, I'm going to go to the categories, which is the language, and I'm going to select group and sort. So now the whole thing is in alphabetical order. Okay, so let's now start having a closer look at this graph and what it's telling us about our word counts. And the first thing that jumps out is how absolutely enormous the number of words for Polish is compared to the other languages. So what our word counts have told us is that this raw word list contains around 4 million words for Polish. But when I looked it up, it's estimated that Polish contains, sort of in terms of like what's in the Polish dictionaries, around 130,000 unique words. So this gives us a strong clue that we're probably going to need to do some cleanup on Polish. And based on my small understanding of Polish, I know that it's a strongly inflected language. That is, there are many different forms of the same word which are used for grammatical purposes. So we might be seeing in the Polish dataset a lot of these different inflections. And then as we saw with that initial count, English has around 460,000 words. This is very high, and it's higher than the estimated 170,000 words that English apparently has. And then Danish also seems quite elevated. The word counts are telling us that the Danish list has around 1.8 million words, when Danish is estimated to have around 300,000 words, although it's a little hard because Danish does use compound nouns, which can grow that vocabulary list. And then on the flip side, a couple of languages seem to have very suspiciously small numbers of words. So for example, Greek is estimated to have around 150,000 words, but the word list only contains 35,000. And Croatian is estimated to have around 200,000 words, but the word list only contains 3,700. So this sort of flags us to, the fact we're using a crowdsourced data set. It's based on sort of the goodwill and efforts of others to build it. And potentially for some languages, there's just sort of not a complete word list yet. And it may also be that with the larger word lists, we're looking at potential quality issues, which we're going to investigate in the next step. But it also kind of points out that it is very hard to get good quality free data. So whenever you're working with a new data set, just be aware of its provenance, be aware of its potential limitations and, where you may need to supplement it or clean it. So I've already mentioned SpaCy a number of times when I've been talking about the packages we're going to be using. But I just want to explain what it is in a bit more detail before we use it for text cleaning. So basically, SpaCy is a family of packages that allows you to do pretty much anything you can think of with natural language processing. That is, processing of text data in natural languages like English. And, some of the packages are concerned with more cutting edge techniques, things like word embeddings, transformer models, word-to-vec. But there's also a lot of functionality for doing classic NLP techniques that are also very powerful. And you can see some of them here. You can do part of speech tagging, you can do named entity recognition, tokenization, things like this. So the technique we're going to be using on our word lists is something called lemmatization. And I'm going to be explaining what that is soon. But for now, understand that it's something that we can use to standardize the words a bit and potentially reduce down the size of those very large word lists that we saw. So in order to lemmatize our word lists, we need to first download language-specific models that SpaCy makes available for each of the languages that it supports. So if we go along to this drop-down menu, you can see that these are the languages that are currently supported by SpaCy. And this is why I chose the subset of languages that I chose, because they have SpaCy models that correspond to them. So because we're asking SpaCy to do a slightly more complicated task, which is to process words out of context, it's also going to be better if we pick a more accurate model. So you can see that there are two options, an efficient model, which is faster, and an accurate model. So I'm going to select the accurate model because it's going to give us better results, but depending on the task, you can also pick the more efficient model. And then the last thing we need to do is to get the specific name of each model for each language, and also this Python command to download them, and we're going to use those in our Jupyter notebook. Okay, so to download these models, the first thing I'm going to do is to create a dictionary which has the name of each model for each language. So you can see that I've just copied and pasted that in there from one that I prepared earlier, and I've just gotten those model names from that web page that I just showed you. And to make this a bit more efficient, because we do have quite a lot of models to download, what we're going to do is set up first a for loop to go over each of the values in that dictionary. And within that for loop, what we're going to do is use the run method from subprocess to execute that same command that we saw on the SpaCy Models website. And basically, this runs this as though we're running it in the command line, but we're running it instead through Python. And then we're just basically going to tell it to give us the output and any errors, and we just set it up to go. So this is going to take a while. So I'm just going to fast forward through until the end. So the first thing we're going to do is to create a directory to contain all of those clean word lists. And we're going to call this data, and we use the make directory method from OS to create that. Then we want to create language-specific folders to contain each cleaned word list. So to get the names of those languages, we loop over the keys of that SpaCy Models dictionary. And on each pass of the loop, we get it to check for that language if that directory already exists. If it doesn't, then create one within the data folder, and if not, throw a file exists error. So let's go ahead and run that, and we can see that that's worked. So we have our directories all set up for our clean data sets. So now that we've finished all of that setup, we're ready to start looking at the data. And we're going to start with the English word list because, as I said, I'm a native speaker, so this is the easiest one for me to inspect. So what we're going to do is first open up the English word list, and we're going to read it in and split it. And so then we end up with a list of words. And then because I prefer always working in data frames, I'm then going to pass that list over to a Pandas data frame. And then if we have a look at that data frame, we can see that we have those 460,000 words. So the reason we can see how many unique values this column has is due to an inbuilt feature in PyCharm's data frames called Show Column Statistics. So let's go up and have a look at our options for that. And we can see that we have the compact view on at the moment, but if we switch over to the detailed view, we can see we get even more information. So we know that each of these values is actually distinct, so we're not going to need to deduplicate this data set. So let's pop the column statistics back in the compact view, and let's now change the number of results that we get returned. So you can see right now, it's returning the first 10 results, but we can actually change that so that we get the top 100. And that's going to give us a pretty good overview of what's going on with this data set and what might be wrong and that we need to fix. So looking at this top 100, we can already see some issues. So the top 4 words are nouns and their plurals. And this might be something that we want to get rid of because language learners might not want to have to learn aardwolf and aardwolves. This might not be that useful. We can also see a large number of names, proper nouns. So some of these might be useful because we might want to know what the place name is in a language. A lot of these are pretty obscure, like Arensberg. This is not really a useful word. And then there are things where we have duplicates, but they're duplicates due to some sort of trailing punctuation, like these 2 ABs. And then we can also see some instances where we have presumably a verb, and it has a lot of different inflections, both in terms of turning it into a noun or, taking the different verb conjugations. And in addition, this particular verb is so rare, I don't actually know what it means. So what we're also seeing is some exceedingly rare words, which again, may not be useful for language learners. So from this initial look at English, we can definitely see that there are some things we need to do to clean up these word lists before we can use them as part of our agent. So let's create a new function. We'll basically turn this little piece of code into the base of our function. And we're going to use this function to load in and do some very basic cleaning on our word list. So the first thing we're going to do is just define that function, and we're going to make it generic for any language. So then we change over our file path so that it's taking in the language as the argument rather than just English. And then what we're going to do is add a piece of code that allows us to do some very, very light and simple cleaning. So in this case, we've seen that we have trailing punctuation, and this is causing duplicates. So we definitely want to get rid of that. So we're going to use string strip punctuation, and we're going to use that just to do some light cleaning. And then we're going to return that data frame, and we're going to just double check that that worked. And we can see that if we scroll down, that has definitely gotten rid of that trailing punctuation on that second AB. So now let's get into a little more advanced natural language processing. And we're going to start with, as I promised, lemmatization. So lemmatization is basically processing words so that you reduce them down to some sort of base form. So we can see 2 examples of this here. We can see it with the top example, which is a verb. We can see that the verb is be, and that is the base form. And there are inflections or conjugations, am, are, is. So lemmatizing am, are, or is would be bringing them back to the base form of be. And in this way, you standardize grammatical inflections, which, we have semantic equivalency between these words, but syntactically, they're different. You can see another example with car. Car is the base form, but we have car, cars as a plural, cars as a possessive, and cars as a possessive plural. So basically, if we were to lemmatize all of these different inflections, these would all come back to car. Again, semantically pretty much equivalent, but grammatically or syntactically different. So we already saw examples of similar inflections in our English data set, like aardwolf and aardwolves comes to mind. And lemmatization is going to help reduce the size of the vocabulary to really just the core words, the base vocabulary, because language learners often want to learn the base form first and then things like plurals later. So the SpaCy models that we download contain a lemmatizer for each of the languages. So they essentially have rules that are specific to that language that will help with language-specific lemmatization. And this is really important because it varies dramatically across languages. And so you really need a good quality lemmatizer to do this accurately. So the next thing we're going to use is something called Zipf's law. And we're going to use this in order to try and get rid of some of those very rare words that we saw, or even words that may potentially be invalid words from our word list. So Zipf's law is a way of describing the distribution of the usage of words in a natural language. And it came from a guy called George Kingsley Zipf. And basically, he was looking at the amount in which words are used in the English language. And what he realized is when he made a table showing how often a word is used and then ranking those, that there was actually a power law to it. So he found that the most commonly used word was actually used twice as frequently as the next most frequently used word. And then the second most frequently used word was used twice as much as the third most frequently used word, and so on and so forth. So this became known as Zipf's law. And it actually is very, very helpful for describing how important words are in terms of usage in language, with him finding that just over 100 English words accounted for almost half of what is actually used in English. So applying Zipf's law to our dataset can help us in two ways. The first way that it can help is that it can essentially identify words that are so rare that they're unlikely to be helpful to language learners. So we can basically get rid of those and reduce down a vocabulary list to more important words. But we can go beyond that and we can actually use it to divide up the language into 3 different bins. So as stated in this article, we can take the upper segment of the curve of the distribution, and these are the most commonly used words. So we can maybe identify those as beginner words. We can take the middle segment, which are intermediate vocabulary, and then we can take the lower segment, which are rarer words, but are likely to be useful for advanced language learners. And in order to apply Zipf's law to our vocabulary, we're going to use the wordfreq package, which we've already talked about. So the wordfreq package has a bunch of vocabulary in a bunch of different languages, and it has the frequency for that. But something that's very cool that's built into it is the Zipf frequency. And the Zipf frequency is basically a logarithmic standardization of the raw count. So it allows us to compare the frequencies between different languages. So we're going to be using that in order to identify very rare words and also create word difficulty bins. We can see that this package supports so many different languages, so we are definitely fine with covering the languages that we've picked, but moreover, you can also expand your language learning agent to these languages if you want to use the Zipf frequency. So let's start by lemmatizing our word lists. And the first step with lemmatization with SpaCy is we need to take those models that we downloaded and load them into a Python variable. And because these SpaCy models come with so much different functionality, we can actually make them a bit smaller, faster, and lighter by disabling functionality that we don't want to use. So in our case, we can disable the parser, we can disable the named entity recognition, and also the text categorizer. Okay, so the next thing we're going to do is to create a function to lemmatize each of the words in the word list. So we're going to call this addLemma, and it's going to take the arguments of the word list data frame, the SpaCy model that's been loaded in, and then also we can process this in batches. So we're going to actually do it in batches of 1,000, and then we're going to return a pandas data frame. So then we're going to pass the word list, the column of the data frame, which is word, turn into a list, through a pipeline attached to the model. And basically we're going to pass that in batches, and that's going to give us back the processed words, which has all of the information that SpaCy extracted for it attached to it. Then what we do is we loop over each of those docs and we just extract the lemma. And then we have those lemmas as a list and we assign that as a column called lemma to the data frame and then return the data frame. So let's now go ahead and test that out. So we already have the previous test that we ran assigning the English word list to the load and clean word list function. So we can actually pass that function to our new add lemma function, doing a nested function call. And we then need to add the other argument, which is the loaded SpaCy model, NLP. And because this can take a while, even with the efficient processing pipeline, because there is a lot to process, we're just going to limit this to the top 100 just for testing. Okay, so let's see how this turned out. So the first thing we can see in the column statistics is we actually have less unique values. So we have actually deduplicated the data set a little bit using this method so far. And the next thing we can see is that the lemmatization has worked in some cases, like aardwolf and aardwolfs, it's worked perfectly, but it's missed other ones like aardvark and aardvarks. And we can also see other cases where it's been a little bit overly aggressive. So in the case of Aaron's beard, this is a plant, it's another name for St. John's wort. It's been slightly too aggressive and done an incorrect lemmatization. And then if we go to the bottom of the list, we have all of these inflections on that verb obeys, the one that I didn't recognize. And we can actually see that SpaCy wasn't able to do anything with this either. So it's likely that this is either not actually an English term or it's so rare that it's not actually contained in the SpaCy model. So we're going to talk about how to address these sort of terms when we come to the word frequencies. But this raises an important point. We are dealing with natural language. This is kind of a hard medium to deal with. And in addition, we've got a kind of challenging data set because, as I said, it's a bunch of words out of context, which is a lot harder for language models to deal with. So understandably, the SpaCy model has struggled with some words, but as you're going to see later on, it's done a very good job with more common words. So let's now move on to calculating the word frequency for each of the words. So we're going to create a new function for this called add word frequencies, and it takes in two arguments. The first is our data frame that now contains the raw word and the lemma, and the other argument is the language that we want to calculate these word frequencies for. So the Zipf frequency method from the wordfreq package takes in a 2-letter language code. So we can actually get that from the first 2 letters of the SpaCy models. So basically what we're going to do is for the specified language, retrieve the value, i.e. the name of the SpaCy model, and then just split it on underscore and take that first element, those first 2 letters. So that then gives us the correct language group in the correct format. So then what we do is for each of the lemmas, we basically pass them through this Zipf frequency method and we attach the correct language group, and that's going to give us the Zipf frequency for each lemma. We attach that as a column to the data frame and then return the data frame. So let's just pop up and copy the code that we used to test out our last function. We're going to paste it here, and then we're going to nest that inside our new function, the add word frequencies one. And then obviously we need to include the language as an argument, so we're going to add English there. Okay, so let's have a look at the results. And the first thing that we can actually see from the column statistics of the Zipf frequency column is that there are many words with a value of 0. And this indicates that these values are, or these words are so rare that they weren't actually found in the vocabulary that came with the word frequency package. We can see also that we have word frequencies that appear to make sense. So the word aardvark or the word aardwolf are not terribly rare, but they're not terribly common either. So it makes sense that they're popping up as, medium rarity words. And then if we want to dig a bit further into some suspicions we had about this word list, if we go down to this a base word with all of its different inflections, you can see that all of them have a value of 0. And this sort of confirms our suspicions, right? This is either a super, super rare word in English, or it's not actually a valid English term. Okay, so between the lemmatization and the word frequencies, we actually have quite good ways of cleaning up this word list now. So I've created this function to do all of this cleanup in one fell swoop. So we're just going to go through step by step what this function does. So the first thing that it does is it deduplicates words that have been lemmatized onto the same lemma, onto the same base form. So we group by lemma, and then what we do is we take the value of the Zipf frequency and we basically just take the max of it. It doesn't really matter which value we take. They're, all going to be the same because the Zipf frequency is based off the lemma, but we're just going to do it that way. And then we're going to reset the index of the data frame because we've gotten rid of some duplicates. The next thing we're going to do is we're going to get rid of all of those words that have a Zipf frequency of 0 because we just don't think they're useful for vocabulary learning. The next thing we're going to do is we're going to create word difficulty bins based on the suggestion of this article about language learning that we saw. So what we're going to do is we're going to say that any word with a Zipf frequency of 2 or less is going to be advanced. Anything from 2 to 4 is going to be intermediate, and anything 4 or below is going to be a beginner word. And then finally, we're just going to do some cleanup at the end. So we're going to drop columns that we no longer need. We're going to drop word because we're using lemma now. And we're going to drop this Zipf frequency column because we don't need the raw numbers anymore. And then we're just going to rename the lemma column as word. And then finally, LangGraph agents tend to work best with data in a JSON format. So instead of exporting it as a CSV, we're going to export it as a JSON. Okay, for the final time, let's copy down that code that we've been using, the nested functions, to test each of our cleaning steps. So this time we're going to nest it inside our cleanup and export function. And this, of course, takes another language argument. So we're just going to add the English as the second argument. So let's go ahead and run that. And to check that it's worked, let's go into the English directory in our new data directory and see what's there. And we can see that indeed it has created this new JSON with the directed name called wordlistclean.json. And if we double click on that and have a look, we can see that it contains exactly what we expected. It contains for the keys an index, and then it contains the words and the word difficulty fields. But of course, calling all of these cleaning steps as a bunch of nested functions is not really the best or safest way of doing this. It's going to lead to a lot of errors. So what we're going to do is bundle all of these functions up into a convenience function called create clean word list. So the first step in this function is to load in the SpaCy model. And then we load in the data set and we just strip off the punctuation. Next, we lemmatize the words and add that as a column to the data set. We add in the word frequencies as another column in the data set. And then we do all those final cleanup steps, basically grouping by lemmas, getting rid of all of those ultra rare words, doing the final cleanup, and then writing everything to JSON. Okay, so let's now go ahead and test this out for real on one of our full data sets. And just to mix it up a bit, let's try it on Spanish just to check that it also works on non-English languages. So we're going to go ahead and call our create clean word list function on Spanish. And this is going to take a while because the lemmatization step can be quite time consuming for these larger data sets. So I'm just going to skip ahead to the end and you can see that it's all done. So what we're going to do is go down now to the Spanish folder. We can see that again, it's correctly created that word list clean JSON. We're going to open that up and just having a quick look through, I speak okay Spanish. I can see that this generally does seem to make sense. So we can feel pretty confident that our cleaning steps have worked pretty well across at least 2 languages. So I've now gone ahead and I've spared you a couple of very boring hours of watching me processing the rest of the word list, and I've done that in the background. So we're now ready to do the final step, which is to check the final word counts. So the first data set that we want to get is the exact same one that we got at the beginning, the number of words in each of the raw word lists. So I actually recycled the same code that we used at the beginning. We have an empty list for the language name and another empty list for the total word counts. We walk through each of the files in that raw word list directory. We get the language name and we also get the count of number of words. And then we save that to a data frame called raw data. And then because our clean data is in a bit of a different format, both in terms of directory and also in terms of the data type, we need to use a slightly different approach. So again, we start with an empty list for the language and for the count of words, and we walk through this data folder. But this time we need to extract the language name from the directory, the subdirectory name. We then go into that subdirectory, load in the JSON, and then count how many keys the resulting dictionary contains. Then we again dump those into the clean data frame. And then we concatenate them into a single data set, which is in a long format. And the reason we do that is it's going to make graphing this quite a bit easier. So again, we're going to go into the data frames chart view, and we're going to group by type. So the type is whether it's clean or raw counts. And then we're going to change the values to the sum. And what we can see here is something very interesting. We can definitely see a reduction in the number of words for each of the languages. So some of these changes definitely seem like they have gotten the vocabulary much more in line with sort of the official vocabulary for that particular language. So for example, English is now down to 112,000 compared to the 170,000 that English is estimated to have. And that's down from around 460,000. So it seems that that has definitely worked. Other languages, it seems to have been a little bit aggressive. So for example, with Polish, the vocabulary is now around 33,000, down from the around 130,000 that is estimated to be the number of words in the Polish language. So this sort of drives forward a very important point, which we've already touched on several times. It is really difficult to get comprehensive, high quality free data, especially text data. And so potentially this source that we have for Polish is not complete. But it could also be that the methods we're using for Polish are too aggressive and they're not actually working all that well. Because I don't speak Polish, I can't actually check this. So in the case that I did want to use this Polish dataset or any of the other datasets where I'm not familiar with the language, it would be really important to try to get a native speaker to at least have a look through and give a sanity check as to whether it looks correct or whether something's gone wrong with the cleaning or whether we need to use an alternative data source. But in terms of what I have seen, I'm pretty happy with the way the English dataset, the Spanish dataset, and the German datasets have turned out. So I speak enough Spanish and enough German to be able to verify those, and I have been able to also run the Spanish dataset past a native speaker. And in addition, the word counts look like they make sense. So we've already talked about the amount of words in our English dataset versus English vocabulary. There's similar sort of cohesion between Spanish and German. So Spanish is estimated to have around 93,000 words in its vocabulary, and we have around 75,000 in our dataset. And German is estimated to have around 300,000 words, and we have around 200,000 words in our dataset. So this is good enough, I think, to go forward with, and we're going to rely on using these 3 languages, English, Spanish, and German, as part of our language learning agent. So now that we have our nice, clean word list, we are ready to start building our language learning agent. So in this section, I'm going to take you step by step through the building blocks of a LangGraph React agent. And by the end of this section, we're going to have a basic agent that can take in a user prompt and return a list of random words. And this is going to be the basic agent that we build upon throughout the rest of this tutorial. However, before we get started building our agent, it's really important that we understand the general concepts behind agents and the LLMs that power them. So this is quite a large, chunky theory section. It's definitely the biggest one in the whole tutorial. But by the end of it, you're going to have a better idea of what agents can actually do, why we choose the particular LLMs that we use with agents, and how you can select the right architecture and models for your agent. So let's get started with the most important question. What actually is an AI agent? An agent is essentially an LLM that has the ability to carry out multi-step processes and use tools to extend the capabilities of LLMs. By themselves, LLMs are really only capable of a basic input-output flow, where you input a prompt and get a single output. Agents extend this using what is called the thought-action-observation cycle, which allows LLMs to take in more complex problems and solve them step by steps. Agentic workflows start in a similar way to regular LLM use, in that users input a prompt. In the case of agents, this is usually a moderately complex problem or task. The LLM takes in the input and starts decomposing the problem into a series of smaller steps. The agent then works through each of these steps using the thought-action-observation workflow. For each step, the LLM will think, in a sense of it, about what it could do to solve the problem, potentially using a variety of tools to achieve this. Then it carries out an action. The agent stores the result of this action in a memory, and this memory state is passed back over to the LLM where it can observe the results. The LLM may then reattempt the same step if the results weren't as expected, move on to the next step, or if it judges that the goal has been achieved, then it ends the agentic workflow. From this basic framework, you can build complex agents capable of doing many things that a base LLM cannot. For example, you can give the LLM access to a wide variety of tools, which greatly expand what your agent can achieve. You can also create your own custom tools. For example, tools for performing calculations. And we'll see a few examples of these in the agent we build during this tutorial. You can give agents access to web search, enabling them to retrieve up-to-date information. They can interact with code execution environments in a controlled way. For example, JetBrains' own Junie coding agent does this. And agents can integrate with MCP servers via the Model Context Protocol, a standardized interface that lets them interact with many external tools and services in a consistent way. We'll also demonstrate how to give our agent access to an external service using the MCP later in the tutorial. In our tutorial, we're going to be building a React agent. React is short for reasoning and acting, and this type of agent allows the LLM to decide which tools to use in which order in order to carry out a goal. They tend to be suitable when an agent needs flexibility. There are multiple different types of user requests coming in, and the agent can establish its own workflows using the tools available. Because getting an LLM to do problem decomposition and create an appropriate workflow is a complex task, React agents tend to work better for smaller, more focused use cases. And just as an aside, I've taken this diagram from Hugging Face's excellent agent course. If you want something to follow up this tutorial with, which goes a little bit broader but not quite as deep, this is a great place to start. And you can cover all sorts of topics like building agents in different frameworks and also topics relevant to productionization. It's also possible to build much more structured agents. You can see this in this tutorial from LangGraph, the agents framework we're going to be using in this tutorial. Here the idea is to build a customer service agent, and there is a very specific workflow that the agent needs to follow to complete incoming requests. The architecture combines some deterministic elements, such as making sure that some tools are used in a certain order with the flexibility of the reasoning model's decision-making, depending on the user request and the outputs of each step. And then finally, when you need an agent to do something really complex, you can consider building a multi-agent application. This allows you to build multiple smaller agents focused on more specific tasks and orchestrate them using a controller agent. Multi-agent applications can also help increase the security of your agentic applications, something we're going to discuss more at the end of this tutorial. So as you can see, agent is a term for a very broad family of applications that uses one or more LLMs to break down problems and use a huge variety of potential tools to carry out user tasks. In this tutorial, I'm going to be showing you the basic building blocks to create one, giving you the foundation to experiment with your own ideas for an agentic application and to keep learning about more advanced architectures. But before we get started with creating our agent, it's important to understand what an LLM is and how it can possibly carry out the sort of tasks that agents do. If you're already familiar with LLMs and reasoning models, feel free to skip this section and jump straight to the code. An LLM is basically a neural network that has learned a lot about how language functions. They're really the latest and most powerful tool we have for natural language processing, from a long line of research that has produced very useful tools like lemmatization, like we saw in the last section. To start explaining how LLMs can learn so much about language, we need to understand a basic building block called word embeddings. Now, to explain what these are, let's take 7 words: king, queen, girl, boy, woman, man, and tree. So let's say we try to manually group them together in a 3-dimensional space based on their similarity. So we put woman and man together, queen and king together, girl and boy together, and off in the corner we put tree. Now, if we take the coordinates of each word, we can see that along this first dimension, girl and boy are similar, but the rest are quite different. So perhaps this dimension represents something to do with age. On this second dimension, queen and king are similar, but they're very different from the rest. So maybe this dimension represents something to do with class or nobility. And finally, in the third dimension, all of the people are similar, but tree is different. So maybe this dimension represents something to do with personhood. These values for each word are word embeddings, and they represent the meaning of a word by grouping words that are similar and creating distance between words that are dissimilar. Of course, we don't create these word embeddings manually. That would be an absolute nightmare, especially for large vocabularies. Instead, we rely on a type of neural network called word embedding models to do this for us, which learn the relationships by seeing how words are used in context. And to demonstrate this, I'm going to show you how a model called word-to-vec works, specifically the skip-gram architecture. The way this model works is it learns the word embeddings by taking all usages of each word in your training data and trying to predict which words are likely to surround it. So let's take the case of the word best. We're going to ask the model to predict which word immediately precedes and follows best. And initially, its guesses are going to be pretty inaccurate, but as it sees more and more examples of sentence fragments containing this word, it will adjust its weightings and its guesses are going to get closer and closer. So let's get to training this model. In our first sentence fragment, the word in front of best is the, and after it is things. In our second example, it's also the and things. However, in our third example, it's the and Halloween. The model is therefore going to predict that the most likely word to precede best is the, and with a little less confidence, the word that follows it is things. The weights that it uses to make these predictions end up being the word embedding for best. And we repeat this exercise for every word in the vocabulary, meaning we have a word embedding for each word in our corpus or body of text. Due to the way that this model is trained, it means that words that are used in similar contexts end up with similar weights in their embeddings. So here you can see that best, worst, and funniest are used in a similar context. And we look at the resulting embeddings, we can see that their embeddings are also similar. But in contrast, words like regulate, audit, and govern are all used in very different contexts. So they have very different embedding weights on each dimension. In practice, word embedding models don't have 3 dimensions or 5 dimensions like I've shown here, but usually 100 or more, maybe 1,000 or more. And in addition, we don't care in principle what the dimensions mean. We only want them to separate out words that are different and group words that are similar. So word embeddings were the hottest thing ever for a while when they first came out. I actually remember using them in my first data science job and being completely fascinated by them. But one of the biggest limitations of word embedding models is that all meanings of a word are collapsed onto the same token, regardless of whether it means different things in different contexts. So an example of this is the word bank, which has very different meanings depending on the context. And we can see that in these 2 sentences. He checked his bank account describes bank in the sense of a financial institution, whereas the riverbank was peaceful refers to a bank as a natural feature. And this is where the latest generation of models come in, which are designed to understand the meaning of a word in context. Broadly, they're based on a type of neural network called a transformer model, and all of the cutting-edge LLMs, like ChatGPT models, Claude models, Gemini, Qwen, and DeepSeek, are all variations of this type of model. So I'm going to give a very high-level explanation of how these models work. So let's start with an example sentence. He checked his bank account. So we start by transforming each of the words into word embeddings, just like we did with the word-to-vec model. We then add positional vectors to each of these embeddings to indicate their position in the sentence. So the embedding for he would be weighted to indicate that this is the first word in the sentence. Checked would be weighted to indicate it's the second word, and so on and so forth. These weighted word embeddings are then fed into a mechanism called self-attention. Self-attention basically uses the information from the weighted word embeddings to understand how much attention it needs to pay to the other words in the sentence in order to get the meaning of that word. So let's break down these self-attention vectors. Each word has its own vector, and let's have a closer look at the vector for bank. Each of the vector elements corresponds to a word in the sentence. So the first element corresponds to he, the second to checked, and so on. And as you can see, the highest values in this vector are for the words checked, bank, and account, indicating that the model has worked out in order to make sense of the meaning of the word bank in this context, it needs to take these words most into account. So you can see that accounting for the words checked and account allow the financial meaning of the word bank to be discovered by the model. As you can see, the self-attention mechanism also tends to focus on the word it's finding context for most strongly, the word itself. As such, the model creates these self-attention vectors for each word multiple times and then averages over them. And then finally, the model does some normalization, which makes it easier to work with the attention vectors. And this process of generating self-attention vectors and then normalizing them is called an encoder block. The attention mechanism allows transformer models to do all sorts of interesting things with text. We can see this in the original architecture of the transformer model, which was designed to translate sentences from one language to another. In order to do translation between 2 languages, a transformer-based model needs 2 components, an encoder and a decoder. As you can see, in both the encoder and the decoder, they're using attention blocks to process the text data coming in. However, their goals are a bit different. The role of the encoder is to learn everything it can about how words in the source language relate to each other, and then send that information over to the decoder. The decoder has a slightly more complex job. It firstly needs to learn everything it can about how words in the target language relate to each other. It then uses that knowledge, as well as what the encoder has sent over about the source sentence, to predict, word by word, the most likely sequence in the target language. So you can see that in this example here. Let's say we have this sentence in English, I have visited Italy, and we want to translate it to German. Now, our encoder will have learned a whole bunch about how English functions, and our decoder will have learned about how German works. The sentence is first processed by the encoder, and then word by word, the decoder generates the corresponding German sentence. Over the past 6 years, the transformer architecture has been so successful that it's led to the development of larger and larger models, which are of course now called large language models, or LLMs. The basic transformer architecture has spun off many different types of models. Some, like the original model, use both the encoder and decoder blocks. Some only use the encoder blocks. And some only use decoder blocks, the so-called GPT family of models, which are the models that are used in agents. GPT models were born from the idea that decoder units on their own are pretty useful. As we discussed, the decoder's whole job is to learn the ins and outs of how a target language works, and then use that knowledge to predict the next word in a target sentence based on an input. Researchers started to think, well, what if we cut out the source language and the encoder, and we trained decoders by asking them just to predict the next word in the same language? What we can do is train these models by showing them millions of sentences in a single language and getting them to adjust their predictions based on whether they can successfully predict the next word or not. And what we end up with as a result is a model that has a pretty good idea of what the most likely words to come next are based on a given text input. So we can see that in this diagram here. We have the input I have, and the model has learned the probability of the next words after that, and then it'll learn the next words following that, and so on and so forth. However, the thing is once you train a GPT model, all it can really do is output the next word. If you wanted to do something useful, like answer questions or solve problems, you need to give it some further training. Now, the most suitable LLMs for agents are reasoning models. So how do we transform our base GPT model into one of these? Well, there are multiple different ways of doing this, but the explanation I'll give here is how the Qwen 3 reasoning models were trained, as we're going to be seeing these later in the tutorial. The base LLM goes through 4 post-training steps. The first is what is called long chain of thought cold start training. The next stage is reasoning reinforcement learning. Then the model undergoes thinking mode fusion before finishing with a final general reinforcement learning stage. Now, this sounds very complex, but I promise I'm going to give a simple explanation of these. So let's go through them step by step. Let's first break down what is happening in long chain of reasoning cold start. So when a GPT model is first trained, all it can do is generate natural text. It doesn't yet have any framework for problem decomposition, that is, taking a problem that requires multiple steps and breaking it down. So this stage is about bootstrapping reasoning from scratch. To do this, researchers create datasets where chain of thought reasoning is used to solve problems, as you can see in the slide. So let's say we have the prompt, Alice, Bob, and Carol are sitting in a row. Alice is not next to Carol. Bob is not at either end. Who sits in the middle? And long chain of thought reasoning would reason through this problem like so. There are 3 sits, left, middle, right. Bob is not at either end, so Bob must be in the middle. Now check the constraint, Alice is not next to Carol. If Bob is in the middle, Alice and Carol must occupy the ends. That satisfies the constraint automatically, therefore Bob sits in the middle. You can see how this is teaching the model to reason through each step of the problem to be more likely to reach a correct answer. Each example in the dataset is like this. The problems all include a question and a detailed reasoning trace before the final answer. The base GPT model is now further trained on this specific dataset, teaching it to output answers more like this. This supervised fine-tuning stage is what gives the model its first thinking habit, so to say. It's still learning by imitation, it's still predicting the next token in these reasoning sequences, but now it begins to internalize the structure of logical thought. So now we have this nice model that's proficient at generating chain of thought reasoning for problems. However, there's no guarantee that the conclusion it comes to are correct at this stage, or it won't get caught in a type of circular reasoning. So the next stage is to teach it how to reason well. And this is what stage 2, reasoning reinforcement learning, is designed to do. So our fine-tuned model is given a fresh set of problems, and it generates multiple reasoning paths for each one, some correct, some wrong. And then these answers are used to train a separate reward model, which is able to predict things like the correctness, the logical consistency, and the clarity of an answer. So once this reward model is trained, it can calculate an advantage signal for each new answer from the fine-tuned LLM. The advantage signal is how much better or worse than the expected answer the predicted answer was. It then updates the weights of the LLM, pushing it closer to more correct and high-quality answers, and further away from incorrect, confusing, or overly long answers. Now we have a model that is very strong in reasoning, but not every problem requires deep, slow thinking. So in order to make the model more flexible, stage 3, thinking mode fusion, teaches it to distinguish between problems that require deliberation and those that can be solved more directly. So here we can see an example of 2 such problems. The first requires the chain of thought reasoning that the model has been taught so far. So if we have a look at this question, a car travels 60 kilometers in 1.5 hours, what's its speed? Prompts the model to think about it step by step. However, the second can be solved directly, meaning that applying deeper reasoning to solve it would be both a waste of time and compute. Keep in mind that chain of thought reasoning uses many, many more tokens than direct problem solving. There are a few different ways of doing thinking mode fusion, but one is further fine-tuning the model. A dataset with a mixture of deep and direct problems is created, and the model is trained to distinguish between when fast and slow reasoning is required. And you can actually see this when we use the Quen model when it has the little think tag that indicates that it's actually doing slow reasoning. And now the final step, general reinforcement learning. So what we now have is a model that is highly specialized in reasoning, but that's really all it can do. So if you want to use it in normal chat, it's likely to be unpolished, maybe even confusing, and it's unable to do other important NLP tasks like summarizing documents. The final step therefore uses reinforcement learning again to now teach the model to only apply reasoning when needed. The model creators developed yet another dataset, this one containing a mixture of reasoning problems and other tasks, such as instruction following, factual question and answering, and creative writing. As with the previous reinforcement learning step in stage 2, the LLM is given the same prompt from this dataset multiple times. This time, the answers are scored based on their quality, a mixture of things like helpfulness, relevance, honesty, conciseness, and reasoning quality. These ratings are done either by human raters or a more powerful LLM in a process called LLM as a judge. And as with the last reinforcement learning step, these answer score pairs are used to train a second reward model, which can predict the overall quality of answers given by the model, not just its reasoning abilities. These scores are, again, used to update the model weights. Answers that produce higher advantage signals, in this case for quality, change the model weights to make the model give answers more like these. And those that produce lower advantage scores, of course, change the model weights to produce answers less like these. So, phew! After all that work, pre-training, fine-tuning, and refining through reinforcement learning, we now have a model that is good at breaking down problems and working through them step by step, and being flexible enough to do some other things as well. But are these models the best models? Should we use them now for everything? Well, actually, no. All of these post-training steps have forced the model into specializing in problem solving, meaning that it might not actually be the best model to use outside of settings where this is really important. So I have here a blog post that I found from Sebastian Rasker. He's a really well-known researcher in AI. And basically, it sums up and explains reasoning models. But what I want to focus on is this really nice table of advantages and disadvantages of using reasoning models. So you can see that as he sets it out, they're really well suited to use cases where complex multi-step problem solving is important, such as when you're using them as the reasoning engine in an agent. But they may actually not be as accurate in other tasks. And in addition, they might be more expensive to use and they might be slower. So we might want to use a different model when we're doing a task that doesn't require heavy problem solving. And we're actually going to see an example of that later when it comes to machine translation. Okay, so with all of the theory out of the way, we are finally ready to get started building our agent. And as I mentioned earlier, the framework that we're going to be using is called LangGraph. Now, this has become a very popular choice for building agents, partially because it's very, very powerful, but also because it's really flexible. So we saw earlier that you can build many types of agents using LangGraph. You can build those more structured agents, which require the LLM to only sort of make decisions at certain points. You can build multi-agent applications. And as I'm going to show you, you can use it to build a React agent. And while we won't cover this in the course, when it comes time to productionizing your agent, LangGraph also has a lot of capabilities built in for testing your agents and also making sure that they run efficiently. So popping back over to PyCharm, you can see that we now have this new script called main.py. And this is the script that's going to hold the main code to run our agent. And the code that we have so far contains the basic building blocks for creating an agent in LangGraph. So let's go through these one by one. And the first thing I want to talk about is this class you can see here, the agent state. Now, at the beginning of this section, when I was introducing agents, you might recall that I mentioned that something they can have is memory, both long-term and short-term. Now, the agent state is a type of short-term memory, sometimes called working memory, which allows the agent to keep track of its progress as it completes each task. Most importantly, what actions it's actually taken and the outcome of each of these. So we talked about that thought, action, observation cycle that agents have. This is what the reasoning model is observing. And the main sort of thing that it needs to get from that observation is working out whether the step it took was successful and it can move on to the next action, whether it needs to retry the current step. And you can see that the only field that we have in the agent state so far is messages. Now, this is a very important field in the agent state in LangGraph because it essentially allows the agent to keep a running conversation history of everything that's gone through the agent so far. So everything that's been passed in, including by the user, and everything that's been output in each step that the agent has taken. So the next thing that our React agent, of course, needs is some tools. So at the moment, I have one custom built tool that I've created called getNRandomWords. We're going to have a look at that in a second. But for now, all we really need to do is to import that and assign that to this local tools list. We're going to see how to make that available to the agent in a second. And then, of course, the next thing that our agent needs is an LLM. So we are going to start by using a model from OpenAI called GPT-4o. Now, of course, this is a paid model. So if you want to use this model, I'm going to show you in the next section how you can get your own API key and how you can set up billing. But if you don't want to use a paid model or you don't want to use a proprietary model, I'm also going to be showing you in the next section how we can use a local free open source model. But while you're still learning what agents can do, GPT-4o can be a really good choice as a starter model. So it has a few strengths. The first is that it's a very powerful reasoning model. And on top of that, it's multimodal. So it can actually take in both text and image inputs. And then on top of that, because it's running off the OpenAI API, it's very fast. You're going to see that when we switch over to a local model, things slow down a little bit. But these sort of things make it a lot less painful when you're sort of iterating through multiple versions of your agent, experimenting with what kind of inputs you want it to have, and just playing around. And then the final and probably the most important component is this assistant function. So this is the heart of the agent. It's basically the infrastructure that allows our reasoning model to act as the reasoning engine in the agent. So basically the job of this function is to take in the information contained in the agent state. You can see that that's basically the argument that it takes. Pass this information to the LLM for processing. Call any available tools to complete the next planned step that the agent wants to do, and then update the agent state following this action. And there's a few important components that this function has to accomplish that. The first is the system message. So basically, this is going to be input as part of the initial prompt to the LLM when we start the entire process. And it's exactly the same as if you're using a chat LLM like GPT or Claude, and you give it a lot of context or instructions to allow it to understand a task you want to do. So we can see here we have some very basic instructions so far. We're really just telling the model that it's a helpful language learning assistant and that we're going to give it some sort of user instruction. But we're going to be expanding on this prompt soon. The next thing we need to do is bind the tools to the assistant so that they're available to it when the agent is running. Naturally, we've already talked about the core component, which is the reasoning LLM. And then finally, we have the return. So what is returned from this function is a dictionary which contains all of the necessary information to update the agent state. So as I mentioned, if we want to use that OpenAI model, GPT-4o, we're going to need an API key for that. And we're also going to need to set up billing so that we can pay for its usage. So the first thing we need to do is to go to platform.openai.com. And if you don't have a user account, you will need to create one. So once you're in your account, go to Settings, which you can reach by clicking on this cog icon in the top right-hand corner, and then go to API Keys. And to create a new API key, just click on this button here, Create New Secret Key. Now, obviously, make sure that this key does not get leaked. If so, people will be able to very quickly use up all of your tokens. Now, in order to be able to use that API key, you also need to load some money onto your account. So we then go down to the Billing tab. So you can see here, this is the amount of credit I have available. I was able to load that money on by going to Add to Credit Balance and basically paying through that portal. So just a few things about managing your money when using LLM APIs, because they do have a reputation for being really expensive. The first is that you can basically prepay a set amount of money. So just do pay as you go, as you can see that I'm doing. Another thing you can do is to set a usage limit. So you can make sure that even if you've loaded up a certain amount of money, you're going to get a notification if you use past that amount of money. The other thing is that while LLMs do have a reputation for being very expensive to use, that reputation really comes from really, really huge models and really, really cutting edge models. So shopping around, looking at different providers, and also considering smaller models or older models that might be fit for your use case can be a really cost-effective way of using these APIs. So now that we have our API key, we need to make it available to our agent. Now, I think it can be quite risky just copying and pasting raw API keys into your scripts. It's very easy to accidentally commit that to GitHub and then expose your credentials. So I really like to use a tool called python.env, which allows you to load API keys in a separate file into your environment. So the code for this is very simple. We just need to import load.env from .env. And then we just need to call the load.env method. Now what this method does is it goes and looks in this special file in our root directory called .env. And it's going to take anything that's in that .env file and then load it into the environment. So basically you can see here that I have my OpenAI API key, and then basically where it says your OpenAI API key here, you basically just copy and paste your own API key. So any other access keys or access tokens that you need to use for your agent can also be put in this .m file. And when you run that load.m method, they're all going to be written to the environment at the same time. So let's now go back and have a look at one of those building blocks of our agent that we discussed earlier, and that is our tool. So this is a custom tool that I have written myself for the agent's use. And you can see that it's in a separate folder called tools.py. You don't have to do it this way, but it just makes it a little bit cleaner to build the application. So first things first, let's look at the actual code for this custom tool. And you might have noticed that apart from the tool decorator, which we're going to come back to in a second, there's no LangGraph specific code here. It's actually just a normal Python function. So going through what it does step by step, basically what it does is that it creates a path for a specific language to that cleaned word list. And then what it does is it opens that word list using the JSON load method. It goes through the word list, and for a given n, it takes a random sample of the words in that word list. And then using a list comprehension, it just keeps the word. It doesn't keep any of the other metadata that we created in that file. And then it just returns those random words. So this is actually really, really powerful because it opens up the full scope of everything we can do with Python outside of LangGraph when we're building our custom tools. And then in order to signal to LangGraph that this is a tool, we just need to import this tool method from langchain.core.tools and use that as a decorator. So one thing that we do need to watch out for when we're creating LangGraph tools as opposed to regular functions is that we need to be very strict with our documentation. So while it's best practices when you're creating a Python function to use things like type hinting or create docstrings, this is absolutely mandatory when you're creating a LangGraph tool. And the reason for this is that when the agent is considering which tools to use, it needs to understand in natural language what the tool does, which is provided by the docstring, and it needs to understand both the input and the output types of each tool so it knows what is a valid input and what the output of that tool has been. So you can see that I've already gotten us started with this tool. I've already put in the type hinting. So for the language argument, I've specified that it must be a string. And for the n argument, I've specified that it must be an integer. And then I have explicitly specified that the output type of this tool is a list. But you might have noticed that I haven't written the docstring yet. And that's because, frankly, writing a good docstring is quite boring and it's quite a lot of work. And if you're going to be creating an agent, you're going to need to be writing quite a lot of good docstrings because the agent really needs them to understand what the tool does. So PyCharm offers us a bit of a shortcut here, and we can actually get JetBrains AI to write the docstring for us. So if we just click anywhere in the tool here and we select Alt or Option Enter, depending on your operating system, we're going to get the AI Actions context menu. So we just go down to Write Documentation. That will be passed over to the AI service, and it will automatically, as you can see, generate the docstring for us. Easy peasy. This saved us a lot of work. And because we should be checking the output of anything generated by AI, we should definitely go over this docstring and just double check that it looks correct. So we can see at the beginning, it has definitely correctly summed up what the function does. So this is great. And then if we go through each of the arguments, we can see that it's correctly specified the type and the function of language and n, and it's also given the return type correctly. So I've been going on and on about how we need to have this information, the docstring and the type hinting in our tool so that the agent knows what the tool does. But how can the agent know this information before it calls the tool? Well, what we can actually do is copy and paste this information, the type hinting, the name of the function, and also the docstring, and include this as part of the system prompt. So we're just going to copy that information from our tool and then head back over to main.py to our assistant function. We're going to create a new string called textual description of tools, and then just paste that information and get rid of any stray quotation marks. Now, creating this string doesn't make that information available to the system message. So we need to pass this string into that system message string. So what we're going to do is to expand our prompt and add the line, "You have access to the following tools." And because we have this already as an F string, we're just going to open some curly braces, pop in that new string, textual description of tools, and this is now part of the system prompt. Something else we can do to help guide the agent is we can add more information to the system prompt about how it should use that tool. So let's go ahead and add these additional instructions, and let's read through them bit by bit. The first thing we're going to do is to be a lot more specific about what we want the LLM to do. So we essentially tell it that its job is to check for the source language that the user wants words from and how many words they want. And then we give a few specific examples of successful workflows. So if we have a look at this first one, we have the input get 20 random words in Spanish, and we told it that the source language is Spanish and the number of words is 20. And that input should obviously mirror what we're expecting our users to input as closely as possible. So this is an example of a type of learning used with LLMs called meta-learning, in this case specifically few-shot learning, where you provide examples of what you're expecting the LLM to produce, and this helps guide the LLM's output to be more like this. So we're now asking our agent to keep track of these two additional fields, source language and number of words. Now you may have noticed these correspond to the arguments for our tool. So this is why we need the LLM to extract them and keep track of them, because when it uses the tool, it will need this information. But if we want these fields to be specifically tracked as the agent works, we need to add them as new fields to the agent state. Now this is very straightforward to do. We simply just add source language, and then we're going to add number of words as new fields or keys in this class. And we give them the optional type because depending on the user query, these particular fields may not be needed. And then because we've added these new fields to the agent state, we also need to add them to that dictionary that is the return of the assistant function. Because remember, the point of the assistant function is to update the agent state every single time it's called. So we finished all of the building blocks for our agent. So now we can finish things off by building the agent graph, passing over a user prompt, and then invoking it. That is, being able to run our agent. So we're going to get started by importing a couple of additional methods. In order to be able to build the graph, we're going to import the following methods. So from langgraph.graph, we're going to import stateGraph and start. And from LangGraph pre-built, we're going to import toolNode and tools condition. So the next thing we're going to do is to bundle up our local tools in a function called setupTools. And you might have noticed this is also an async function. So this seems a bit like overkill because this is not going to affect how these tools are called because they're local. But basically down the road, as I mentioned, we're going to use MCP. And basically this needs to discover tools from the server asynchronously. So if we make this function and some of the downstream functions asynchronous now, that's going to save us some refactoring when we get to that point. So now we're going to create this build graph function. And this function brings everything together and it converts our assistant function from just a simple function into an agent. So the first thing we do is we call our tools by calling that setupTools function. And then we assign those tools to that assistant function. We then instantiate a new LangGraph state graph, a new agent, assigning it the agent state as its argument. So now that we have this state graph object, this agent object, we can start building out the graph by adding nodes and edges. So based on the diagram that we saw earlier, this only has two nodes, the assistant node and the tools node. So we're going to go ahead and add those. So now that we have our nodes, we need to connect them, and these are our edges. So the first connection is from the start to the assistant. So our starting point is the entry point, the initial prompt that goes into the LLM. And that's going to be a combination of the system prompt that we've been creating so far and a user prompt, some sort of user instruction. The next connections are between the assistant and the tools. So we have one edge here, which is just a straight connection between the tools and the assistant. We know that they need to be connected because we need to be able to go between the assistant and the tools that it needs to use. But then we also have this conditional edge, which basically allows the LLM to decide whether it needs the tools or not for a particular action. And that's it. As we saw in the diagram, this is a really, really tiny graph. So we really didn't need much to build it. And that's because this is a React agent. We're essentially allowing the LLM to do the planning and decision-making when it comes to solving this problem. And then to finish this function, we just need to compile that graph and return it. And now we need just a little bit more code to actually run our agent. So we're going to create a main method. And inside our main method, the first thing we're going to do is to call that build graph function. So for the next step, we're finally at the point of getting to decide what we want our agent to do for us first. We get to enter a user prompt. So let's try out our agent with please get 10 random words in German. Then we take that string from the user prompt and we assign it to a human message. Now, this is a distinct type of input into the LLM from the system message that we've been creating so far inside the assistant. And it indicates to the LLM that this is the specific instruction input by the user. And then the final step is that we're going to invoke the graph. A invoke in this case, because we are invoking it asynchronously. And you can see that when we invoke the graph, we pass in a dictionary with 3 keys. And these line up to the 3 fields that we have in our agent state. You can see that the value of messages is set to that user input, that basically the user prompt converted to a human message. But in the case of source language and number of words, they're left blank. And that's because if there's any value for the agent to discover as it iterates through the problem, they will be assigned at that point. And then finally, we are ready to run that main method. And we're again going to run it asynchronously because that's how all of our functions have been defined. Now there's just one more step before we can run our agent with our example prompt. And that's to talk about some tooling that can help us see what's happening inside our React agent as it's running. So something you might have been wondering about React agents is how do you actually debug them if the entire workflow is decided and managed on the fly by the LLM? And that's where the AI Agents Debugger comes in, which is a plugin that's available in PyCharm. So opening up this plugin, we can see that it's designed to show traces from LangGraph agents. And what that means is that as your agent is executing, it's going to show you the steps and the decisions that the agent is making as it executes. And that's going to be shown right within the IDE and locally. So in order to use the AI Agents Debugger, we first need to install it from the JetBrains Marketplace. And we can reach this through the plugins settings. So we can access this in a number of ways. My favorite way is to press Shift-Shift within the IDE, type in plugins, and select this welcome screen option. And then this opens up the plugin settings, and we can simply search for the AI Agents Debugger within Marketplace. You can see that I already have it installed. But if you want to install it yourself, you just go to the Marketplace tab, type in the name of this plugin, and then select to install it. So finally, we are ready to run our agent for the first time. So in order to do this, we are going to run our main.py script from the execution point. And you can see that once we do this, our AI agent's debugger automatically detects that a LangGraph agent is executing and starts displaying the traces. So if we have a look at the output for the AI agent's debugger, we can see that the first step that the AI agent has taken is a tool call. And that's obviously our get n random words tool because it's the only one we have. And if we have a look, it's correctly parsed the inputs that it needs. It's parsed that the correct language is German and that n is 10. And then we can see from the AI agent's debugger that the output of that tool call was indeed a list of 10 random words in German, exactly what we would have expected based on the output type for that function. So one other nice feature I want to show you within AI Agent's debugger is the graph view. So if we go up to this toggle button, this will switch us from the events view to the graph view. And you can see here that this is the structure of our LangGraph agent. And you may have noticed this looks pretty much identical to the diagram we saw of a React agent in the Hugging Face tutorial. So this gives us a sanity check that we've actually constructed our agent in the way that we intended to. And in this case, we have. This is a very typical React agent setup. So we now have our basic agent, which is running off the back of a proprietary model, which is managed by a third-party company. And while using these sort of proprietary models for agents is very convenient, they're very fast, they tend to be very powerful, they do also come with a number of downsides. The first of these, of course, is cost. So we've seen that we need to pay for these models, and because agentic applications in particular tend to be very token hungry, the cost can add up rather quickly. Another important consideration is data privacy. Now, depending on the data that you're using in your agent, you may not want it sent to a third-party provider, especially if your contract for using the LLMs allows them to use your data for training further models. And a final important consideration is using the right model for the job. So LLMs have just been growing and growing. We know this. And we have gotten really used to using these huge, potentially overpowered LLMs for every use case, when potentially we could use a smaller, more focused LLM that would do just as well. So using a smaller LLM that is trained for your specific use case has a number of advantages. It can save you in costs, it can save you in GPU utilization, and it can also make productionizing your agentic application much simpler. So in this section, we're going to be exploring using smaller open source reasoning LLMs to power our agent. And to do this, we're going to be using a tool called Ollama. So Ollama is a very popular tool for running LLMs locally. So people might prefer to run LLMs locally for a number of reasons. It might be for cost reasons, it might be for privacy reasons, or it might be because they just prefer to use open source models compared to closed source models like the one we were using in the last section. So because Ollama models are specifically designed to be run locally, they tend to be very lightweight models compared to these absolutely enormous closed source models or proprietary models that we were using in the previous section. So this is through a combination of two things. Firstly, the models that are available on Ollama tend to just be smaller variants. So something like 3 billion or 8 billion parameters compared to, the hundreds of billions of parameters that closed source models tend to have. And the other way in which Ollama models are made smaller is through a process called quantization. So this is basically where the model weights, that is, the numbers that the model has learned during training, are reduced in precision. And basically what this does is it reduces the memory use and also speeds up the model, but it tends to not really impact model performance that much. So apart from having a really large number of lightweight, powerful models available, Ollama is also very popular because it comes with a very clean command line interface. And this allows you, as we're going to see soon, to very easily access and manage the models. But before we can start using Ollama, we need to install Ollama. And the easiest way to do this is by going to the official Ollama website and installing the version specific for your operating system. So you can do that by going to ollama.com/download and selecting the correct version for your computer. So now that we have Ollama installed, we can check out the models. And in order to do this, we head over to the models section of the website. So looking through this section, we can see that there are very powerful and well-known models available through Ollama. Things like GPT-OSS, Qwen3VL, and DeepSeek R1. So you're definitely spoiled for choice in terms of the types of models that you can use through Ollama. And then because we need a reasoning model, we're going to filter these models by the thinking filter, which is the same as reasoning models. So we have quite a few choices of models here, but based on earlier experiments that I did when setting up this project, I've settled on Qwen3 being the best choice for this React agent. And based on the specs of my computer, the 8 billion parameter model, this one here, Qwen3 8B, is around the biggest that my machine can comfortably run and still produce close to real-time results. But you might have a more powerful machine than me. You might be able to use a bigger variant. You might need to move down to a smaller variant. It's just about experimenting with what your machine can handle. So let's now start getting hands-on with Ollama. So we're going to go back to PyCharm and we're going to open a new terminal window. And the first thing I want to show you is all of the models that I already have installed. So we just type in the command Ollama list, and that's going to display all of those models for us. And this offers us a very convenient way of seeing which models we've already got installed. And in the case of models that we might have installed and we're not using, maybe giving us a hint that we might want to delete them, because you can see that some of these models are pretty big. But the other thing you can see from this list is that I haven't yet installed Qwen3. So I'm going to show you how to do that, and this generalizes to any model that you want to pull. So in order to download, or in the parlance of Ollama, to pull a specific model, you go to that model's page, and then importantly, you click on the specific variant that you want to download. In our case, we want to download the 8 billion parameter model. So towards the top of this page, you can see a command, Ollama run Qwen3 8B. So this is actually the command for running models that you've already downloaded or pulled onto your machine. So it's not the exact command that we need, but importantly, this gives us the exact correct name of the model that we need in order to pull this model. So what we're going to do is copy this command, and we're going to modify it slightly in order to be able to pull this model. And then if we copy and paste that command into the terminal and change run into pull, I told you it was a slight modification, this is going to allow us to download that Qwen3 model. So if we just press enter and execute that command, it's going to start downloading that model for us. And as you saw, this is a 5 GB model, so it's going to take a little while. So I'm just going to fast forward through and get us to the end of that download. And then if you want to get a different model, it's really just a matter of repeating the same steps. So from the Ollama website, you get the exact name of the model, you pull it using Ollama pull, and voila, it will just be available on your machine, just like Qwen3. Now, before we change our agent over to using Qwen3, we can actually get a sense of how it's actually going to perform compared to our previous model, the GPT-4o model. And to do this, we can use another tool window in PyCharm called the AI Playground. So let's open up the AI Playground and click on this New Playground button. And we can see that the AI Playground allows us to input 2 different pieces of information. It first allows us to import a system prompt, i.e. a prompt of instructions that we're using to test out an LLM. And it also allows us to add multiple models that are going to run that system prompt. So clicking on this Add Model drop-down menu, we can see we have a huge number of different models that are available to us. And something that's really nice with the way that you access models through the AI Playground is that for proprietary models, you've got a choice of either accessing them using your own API key or through your AI Assistant subscription, your JetBrains AI account. So if you want to quickly try out a proprietary model that you don't yet have an API key for, something like, say, the Anthropic models, you can quickly try them out using the tokens that you've purchased through your JetBrains AI plan. So I'm going to show you how to use this method in order to test out GPT-4o. And then, of course, the other model that we want to compare it with is our Ollama model, Qwen 3 8 billion. So you can also see that without us doing anything, the AI Playground has automatically detected all of those Ollama models that I've downloaded. So it's just as simple as selecting it from a list. So as for the system prompt we're going to provide to these LLMs, unsurprisingly, we're going to use the same system prompt that we're already using in the assistant function of our agent. But because this prompt tells the LLM that it's going to get a command, we need to then provide a user command at the end of that. So it starts exactly as it appears in our agent system prompt. You are a helpful language learning assistant. You have access to the following tools. And then we have that description of our tool, the get and random words tool. Then we have our more detailed instructions that the job of the agent is to check the source language and how many words that the user wants. And then we have those few shot examples of how the agent output should correctly work. And then we add that user command to the end of the system prompt. Please give me 5 random words in English. And then we just finish off this prompt by tying everything together and asking the LLM, how would you solve this problem with the available tools? So just scrolling around and looking at the initial outputs, we can see that both of the models are actually creating their outputs pretty quickly. And as I said, this was one of the reasons that I picked the 8 billion parameter Qwen model, because it can run this fast on my machine. I tried a few larger models and they were definitely a lot more sluggish. But having a closer look at the results from Qwen 3 first, you can see this is a very verbose model. You're going to see this as we're looking through the results. But basically, what Qwen does in its outputs is it shows you very explicitly the reasoning process that it's going through. So essentially, it's saying what the user's input is 5 random words in English. The available tool it has is get n random words. These are the parameters that it takes. So basically what it needs to do is to extract the number of words and the language from the user prompt. And so it's done that correctly. And then it just sort of continues spelling out how it would do it. But this is essentially very much correct. And so it's done a good job. And we can see that it can handle, so far at least, the task that we're getting the agent to do. So the output from GPT-4o is a lot more succinct. We've already seen that when we ran the agent the first time. But basically, it's following the exact same steps and extracting the same information. So it's determined that the first step is to parse the input to extract the source language and number of words. It's correctly identified that source language and number of words. And it's also correctly identified that it needs to use the get n random words function. So this is exactly the same as what Qwen 3 decided. And it really shows us that for at least the tasks we're getting the agent to do so far, there's pretty much an equivalent performance between the two models. So we can feel happy moving forward and changing the agent over to Qwen 3. So it's been pretty straightforward so far to get the models, and changing our agent over so that it uses an Ollama model rather than an OpenAI model is similarly straightforward. So the first thing we need to do is to change the method that we're going to be using to use our model. So previously we were using the chat OpenAI method from the LangChain OpenAI package. We're going to change that to the chat Ollama method from the LangChain Ollama package. And then we go down to where our LLM is defined inside our assistant function. And we keep the same variable name of LLM, but we change it to a call to chat Ollama, and we define the model as Qwen 3 8 billion, again with that exact same format that we got from the Ollama website. So that's it. We're now ready to run the agent again and see how the Qwen model goes in action. So to do this, we go down to, again, the execution point at our main method and run that main script. So we can see that it's taking a little bit of time to think. but now it's given us the first step that it's taken when trying to carry out this command. So our input, of course, is that user input, please get 10 random words in German. And on this call of the assistant, Qwen3 has reasoned through what it needs to do. So it's basically checked the tools available, found the get n random words function, realized that the parameters needed are language and n. It's extracted those successfully from the text, and then it's done a tool call using those arguments. And then, as with GPT-4o, it's correctly done that, and the output of that tool call is that list of 10 random words in German. And then again, just like when we ran the agent with GPT-4o, it's realized at this point that it's actually completed the task when it's observed the results, and therefore it's terminated the agent and given us that formatted list of German words. And with that, we're done. We've finished everything in this section. So we've now successfully changed our agent over from using a paid proprietary model to one that's free, local, and open source. And even better, the performance pretty much looks to be equivalent as when we were using GPT-4o. So in the next section, we're going to start expanding what our agent can do. And we're going to start challenging our reasoning model a bit further by introducing another custom tool. So right now we do have an agent, but it is a very basic agent indeed. It has access to one tool, and all it can do with that tool is to retrieve a list of random words. So you might be thinking back to the second section when I talked about how powerful agents can be and thinking, well, this doesn't look very powerful. How can we get from this basic functionality to something more interesting? So that's what we're going to be doing in this section and in the next two. We're going to be incrementally introducing more tools to our agent, and those tools are going to grow in complexity as we go. So it's really going to expand the range of functionality that our agent has. And in this section, we're going to build another custom tool that allows users to filter word lists by difficulty. And that's based on those difficulty labels that we assigned to the words in the first section, based on the Zipf frequency. So this is a really interesting tool to introduce because it kind of forces the reasoning model to really carefully parse the user input and make a decision about whether they're mentioning a random word list or one that has a difficulty level. So let's look at our new custom tool that we've written that's going to allow the agent to source words by difficulty level. So you can see that we're back in our tools.py file, and you can see here that we now have a second tool, get n random words by difficulty level. So if we have a close look at the code for this tool, we can see that it's very, very similar to the code for our previous tool. In fact, it's a modification of the code for that tool with a filter added in for word difficulty. So let's go through this code step by step. So the first thing that we have a look at is the arguments. So again, we can see that we've set the type hints for each of the arguments as is required by LangGraph. And we can see that we have the same language and n arguments as we had in the previous tool. But we now have this new argument difficulty level. And the return type is again a list of random words, but this one will be filtered by difficulty level. And getting into the function, we can see this looks very familiar. We first create the path to the data file using the specified language. We open that data file using JSON load. But this time we have this new line which allows us to filter the words by difficulty. So we essentially have this dictionary comprehension which allows us to get that word difficulty key and then filter it by the specified difficulty level. And then after that, the rest of the code is identical to the previous tool. We pick n random words from that filtered dictionary, again using a dictionary comprehension, and then we keep only the words in a list from that random word dictionary. And then we just return those random words. And then you might have noticed that, again, this tool does not yet have a docstring, which it does need for being used in a LangGraph agent. So I don't like writing them, as I said earlier, so we're going to, again, get the help of JetBrains AI Assistant. So we'll select Write Documentation from the AI Actions context menu. And again, you can see that it's writing that documentation for us. So as I said earlier, we never accept anything that LLMs give us without first inspecting it. So let's just check that this docstring makes sense. So scanning the opening of it, the description of the function, this makes total sense. This is exactly what this tool does. Then if we go through the section describing the parameters, we can see that this time it's actually separated out the description of the arguments and the type. This is fine. In the previous docstring, it bundled them together. This isn't going to affect the performance of the agent. And you can see that it's correctly identified each of the input and output types and both the arguments and what is returned. So this all looks totally correct. But there's one very important piece of information that we need to add to this docstring, which the LLM creating the documentation didn't have access to when it wrote this. And this is the valid values of difficulty level. So because we have these hard-coded in our data set, there are only 3 valid values that can be passed as the value of the argument difficulty level. And these are beginner, intermediate, and advanced. So we're going to go ahead and add those. And adding this specific instruction to the docstring means that essentially, if our user does not use this specific word, they use something like hard or basic or easy, the LLM can try to look for the closest approximation when the agent is going through and trying to evaluate what arguments it needs to pass into this tool. So now we're going to go through and we're going to add this new tool to our agent. And this is basically a template that you can use for adding any new tools. It'll be the same steps for every single one of them. So the first thing we obviously need to do is to import that new tool from the tools file into our main.py file. And then, of course, now that we've imported it, we need to add it to the list of local tools. So we just pop it in that list with get n random words. So as we already discussed when we were looking through this new tool, it takes 1 extra argument compared to get n random words, and that's something indicating the difficulty of the word. So because we have this new extra parameter that we need to keep track of, we also need to add this to the agent state. So that's something that the agent can keep track of as it's going through and evaluating the prompt. And then the next place that we need to update this is as part of what is returned from our assistant function. So basically, let's go down and add this word difficulty as a new key in the return dictionary. And just to remind you of why we need to do this, it's because the entire goal of the assistant is to keep track of the agent state. So after each time it runs, it needs to update the agent state with things that it's discovered. And then finally, we need to add this to the fields that we invoke our agent graph with. So again, we need to add this in as a field, as a key in this dictionary, but we need to leave the value as none, as this is something that's going to be potentially discovered and populated as the agent runs and processes the input. So the next thing we need to do is to let our reasoning model have some information about what this new tool actually does. And so the first thing that we're going to do, just like we did with the previous tool, is we're going to pop back over to tools.py and we're going to copy the description of that tool, the name, the input and output types and arguments, and also the docstring. And we're going to head back over to main.py and paste that inside that textual description of toolstring inside our assistant function. So this information, to remind you, will now be included as part of the system prompt to the reasoning model. And then we're going to expand the instructions that we're providing in the system prompt. So far we have these 2 points, the source language and the number of words. But now we're going to add in this 3rd point, whether the user wants words of a specific difficulty or just random words. And what this is an instruction to the LLM to decide which of the 2 tools to use, get n random words or get n random words by difficulty. And then finally, let's update the examples that we're providing to the model that it can use for few-shot learning. So we have this last example, which is for getting 10 random words in German. So what we're going to do is change random into hard. And you can see that I've deliberately used a term that's not one of the accepted difficulty levels. And then we add this new field that it needs to extract, word difficulty, and we've mapped hard to advanced. So this will give a nice example that the model can use for this new tool. So the last thing we need to do is just update our user prompt so that it now incorporates this new difficulty level argument. So let's change our current prompt into 10 average difficulty words, and we're going to change the language over to English. And the reason that we're going to use average difficulty is because, again, it's going to require the LLM to do some mapping between this term and intermediate. So we go ahead and we run our agent now, and we just wait a little bit while it processes this more complex input. Okay, so we're getting some initial outputs here. So let's have a look at the first step that the agent has taken. So it started breaking down the prompt based on the fields that are in the agent state. So it's basically seeing that the source language mentioned is English and the number of words is 10. And it's also correctly flagged that a difficulty level is mentioned, and this is average. It's also worked out that it needs to use the get n random words by difficulty level tool, but this only accepts beginner, intermediate, and advanced as valid difficulty levels because we are very explicit about that in the docstring. So then it goes through a bunch of reasoning steps to try and work out, is this mapping to intermediate? Is it a typo? And it comes to the conclusion that it likely maps to intermediate. So the model has come to the conclusion that it is the correct approach to call get n random words by difficulty level and pass in English, intermediate, and 10 as the arguments. And so scrolling down, we can see that it has done this tool call with those arguments. And then scrolling down to the output of that tool call, we can see that it's exactly as we expected. It's a list containing 10 random words in English of an intermediate level. And then, as with the tool call for the get n random words, it basically just gives us that list of words formatted. So let's now try a second prompt. Let's change it to get 30 basic words in Spanish. So again, we're hoping we're going to force the model to recognize that basic is the difficulty level of beginner. So we run our agent and wait a little bit again while the model processes this more complex request. And now we can see the initial steps that are coming out. So the way that the model parses this request is very, very similar to how it parsed the previous request. So I won't go into as much detail this time. But the main thing to look for in this output is that it's managed to correctly identify that the source language is Spanish, that the number of words needed is 30, and it has been able to map the term basic words to the difficulty level of beginner. And then it's correctly again identified that the right tool to use is get n random words by difficulty level, passes all the correct parameters in, and then does that tool call. And again, it's given us the correct output from that tool call. We have a list of 30 beginner words in Spanish. And then again, it's detected that it's successfully achieved its goal. So it's ended the agent run and formatted that list of words for us. And then the final thing we should actually do is a sanity check to check that adding this new tool didn't break the agent's ability to use the old tool, the one that just gets random words. So we're going to change the user prompt to get 5 random words in German and see how it goes with this. So again, we run the agent and then we have a look at the steps that it's taken. Now this is very nice. Even with the introduction of this new parameter of difficulty level, it's been able to ignore that and realize we just want random words. So basically, you can see here that it explicitly says this. Since the user didn't mention difficulty level, I should use the get n random words function. So it's correctly identified the right tool call. It's correctly identified that the source language is German and the number of words is 5. And so it's done everything correctly. It's basically not been distracted by the introduction of a new tool. And when we scroll down, we can see that the output of that tool call is correct. We have 5 random words in German in a list. And of course, the assistant has observed that this has fulfilled the user request. So it ends the agent run. So we're building an agent for language learning. So it's not really that helpful to have random lists of words without translations. So this is what we're going to do in our next tool. We're going to build a tool that can take in words in a source language and translate them to a target language. So we're going to be creating another custom tool in this section, but this one is much more complex than the previous two. This one is actually going to call its own LLM in order to complete the translation task. Another thing we need to handle in this section is getting unstructured output from an LLM when we need something in a specific structure, how we handle that and how we parse that. And then finally, we're going to see how our React agent deals with having to do multiple steps that require a specific order. So something we discussed in quite a lot of detail in the second section of this tutorial is the strengths and weaknesses of reasoning models. And as we saw in this blog post by Sebastian Rasker, while they're really, really good at things like complex decision-making or chain of thought reasoning, which makes them great as the reasoning engine behind agents, they may not be the most suitable model for other natural language tasks. In fact, they may actually perform worse. They may hallucinate more. And in addition, they may be slower and also more expensive to use. So our translation task is going to be faster and more accurate if we use a model that is specifically designed to be good at doing translations. And when I looked around for which model we could use for machine translation, Llama 3.2, in particular the 3 billion parameter variant, kept being recommended as an excellent model for machine translation across a wide range of languages. So of course, if we want to use this model, we first need to pull it onto our machine. So we're going to do that the same way that we pulled the Qwen 3 model by copying this command, Ollama run llama 3.23b. So popping back over to PyCharm, we're going to open up a new terminal window and paste in that command. And then again, we're going to change Ollama run into Ollama pull. Then we're going to go ahead and execute that. And again, even though this is quite a bit of a smaller model than Qwen 3, this is still going to take a while to run. So I'm just going to fast forward through that and see you at the end. So now that we have our translation model downloaded, we now need to create a tool that can use it. So we're going to pop back over to our tools.py script. So the first step in creating our translation tool is initializing the Llama 3.2 model as a translation model. And we're doing that using the chat Ollama method that we also use to initialize our Qwen 3 model. So now that we've done that, let's have a look at our new tool called Translate Words. So this tool takes 3 different arguments. The first argument is a list of random words, and this is the list that we're expecting to come out of the 2 previous tools. It has a source language argument, which should be extracted as part of calling the 2 previous tools. And there's a new argument, target language, which is the language that we want to translate this list of words into. And then it returns a dictionary of words and their translations. So now we come to creating the prompt, and we have a little bit of a tricky task ahead of us. So LLMs generate open text. There's basically few restrictions on the format that text can take. But we essentially want it to return something in a standardized format, something that we can basically represent as a dictionary, mapping words and their translations. So we're going to do our best to try and get the LLM to return us this as part of the prompt. But then we're going to be creating a whole bunch of code in order to process that output just to make sure we've gotten what we expected. So let's go through this prompt bit by bit and see how we try to achieve this. So we start by telling the LLM that it's a precise translation engine and to expect a list of n random words that it should translate from the source language to the target language. And this is where we try to really restrict the output. We tell it only return valid JSON with this exact structure. We basically have a key for translations, and within that is a list of dictionaries which contain the source and the target language. And then we add on an extra little instruction with the hopes that this will actually control the output. No explanations, no extra fields, no markdown. And then we pass in the list of words. Now, I can tell you through experience with LLMs in general and with this specific tool, that does not really work. So we're going to have a bit of code later on to basically try and parse out that dictionary from whatever it returns us. The models can't help themselves. They often have some sort of elaboration like, here is your dictionary. So we're probably going to need to extract the data that we actually want from the output. But the first thing we need to do is to pass this prompt containing the random word list at the end to the translation model, and then getting back the response. And then we optimistically try to parse this output directly, assuming that it has returned valid JSON. But in the case that it hasn't and it throws an exception, what we do is we use good old regex, and we basically search through the text for where the curly braces begin and end, and we extract only the text contained within those braces. And chances are, I've tested this many times, this is definitely going to be valid JSON containing those translations that we want. So after successfully parsing the output of the LLM, what we're assuming we're left with is the dictionary we asked for. So the key is translations, and the value is a list containing dictionaries, which each contain the source word and the translation. So in this next line here, what we're attempting to do is retrieve all of the values for translations. That is that list containing the source and the translations. And if it's unable to do that, then it just returns an empty list. And then what we do is we simplify down this structure to a single dictionary. So what we do is we use this dictionary comprehension to loop over each of the items in the translation list. So each of those dictionaries containing the words and their translations. And we create this simplified dictionary, which uses the original word as the key and the translation as the target. And then the final check we do is just to make sure that each of the words in our original word list of random words that were passed into this function have actually been translated. LLMs are not deterministic, they do make mistakes, so it's really important to do checks like this. So we essentially loop over each of the words in the random words list, and we just check that it exists as a key in this dictionary. And then we essentially return pretty much the same structure that we originally asked the LLM for, but it has been sanitized and checked. And that is a dictionary which has the key translations, and then the value is a list containing the dictionaries of those translations. So now that we've created our next custom tool, we need to add it to the agent. And you're going to see this process is identical to the way that we added our two previous custom tools. So as such, while I'll go through each of the steps, I'm not going to spend as much time explaining them as I did in previous sections because we already know how this works. So the first step is importing our new tool from agent.tools. And then we add it to our list of local tools. And then our new tool comes with an additional field that we need to keep track of in the agent state, and that is the target language. So we're going to go ahead and first add that as a field in the target language. And again, this is an optional type because we may not end up needing to translate the words based on the user's prompt. As we've added a new field to the agent state, we also need to include this as one of the keys in the return dictionary from our assistant function. So we're just going to go ahead and do that. And the final thing we need to do is to add it as a new key in the dictionary that we use to invoke the graph. And of course, this has a value of none as well, because when we invoke the graph, we don't know what the value is going to be. The next step with adding a custom tool is making sure that our reasoning model knows what that tool can do when it's having to make decisions about which tools to use. So we do what we did with the two previous tools. We pop back over to our tools.py file and we copied the description of that tool. So the name, the arguments, and also the doc string. And then we head back over to our main.py script. We head down to our assistant function, and then we paste that information into that textual description of tool string. So that information is now available to the reasoning model when it needs to consider what tools to use. So because this new tool gives our agent additional capabilities, we also need to expand the instruction set that we give to the LLM in the system prompt. So we're going to add a new line in this checklist that we've given to the LLM. And the fourth point we're going to add is whether the user wants these words translated to a target language. And then we're going to round out those instructions in the system prompt by adding some additional examples. So let's copy this last prompt and let's just modify it a bit and update it. So we're going to change hard words to easy words. Let's change German to English. And let's now add the additional instruction to translate those words to Spanish. So that means that the source language is now English. Let's actually make it 15 words rather than 10, so we're not repeating things in the examples. So the number of words is 15, and the difficulty is, of course, beginner. And then, of course, we need to add this new field. So we need to add the target language as something it needs to extract, and this target language is Spanish. So let's try one more example. So this time we're going to make it 50 words. We're going to make them random words. We're going to change the source language to German, and then we're going to change the target language, the language we want it to translate to English. So our source language is, of course, German. The number of words is 50. We get rid of the word difficulty argument because we don't need it. And then the target language is English. And I hope this has shown you that expanding the functionality by adding custom tools to your LangGraph agents is actually really straightforward. So the tools themselves can get complex, like this translation tool that we created, but the actual process of adding these new tools is just a few small changes, and it's this very kind of formulaic, predictable workflow, which just involves expanding the system prompt, adding in additional fields to the agent state, and making sure that all your tools are added in the right place. So now it is time to yet again test out our agent. So we're going to pop down to our main method and, of course, update our user prompt with this new functionality for translation. So in this run, we want to test out the workflow of getting words by difficulty level and then translating them. So our prompt is, please get 10 advanced words in German and translate them to English. So then we go ahead and run that agent. And you can see that as we've added complexity to the agent, it's taking more time to process these inputs. So the agent started giving us some output. So let's go through and have a look at that. So looking at the reasoning steps that the model is taking, it has first determined that the function that it needs to use is to retrieve random words by difficulty level. And it's correctly identified the parameters, that the language would be German, the difficulty language would be advanced, and N would be 10. And then it has actually also correctly determined that the next step is translating them to English using the translate words function. So it's correctly identified the source language as German, the target language as English, and that it needs to use the list of random words output by the previous function. So we can confirm here at the end of this first step that it's going to do two tool calls. It's going to first call get n random words by difficulty level, and it has all of the correct parameters there that we'd expect. And then it's going to call translate words with the words from the previous step as a sort of placeholder, and then the source language is German and the target language is English. So this all looks exactly like what we'd expect. So if we scroll down a little bit further, we can see that something rather weird seems to have happened. So while the agent understood that it did need to call the tools in this order, and that it should have used the output of the first tool call as the input for the second tool call, it actually seems to have used the placeholder word list that it created earlier as the input for the second tool call. And then it seems that it observed this, realized it wasn't right, course corrected, called the translate function again, and got the correct list of translations. And you can see that we have them here at the bottom. And I think this is also a good lesson about the potential downsides of building agents. So while they can be very flexible pieces of software, they also come with the trade-off of being unpredictable. And I think it's really easy to forget that when you see like really slick demos where the agent works so well that it almost looks like magic. But it's really important to keep in mind that we're dealing with a non-deterministic system here, and we need to take the trade-offs that come with that. So let's go ahead and try one more user prompt. So we'll try, please get 30 basic words in English and translate them to Spanish. And we go ahead and run that. And again, we just need to wait for a little bit. So let's go ahead and have a look at what the agent has returned. So it's correctly parsed the user prompt. So it has mentioned that the user has mentioned basic words, which are beginner level words. So it needs to use the N random words by difficulty tool. And it has correctly surmised the parameters, which is the language is English, the difficulty level is beginner, and N is 30. It's then also understood that the next step is translating the words to Spanish using the translate words function. So just like last time, it has been able to correctly parse the input and work out the correct tool calls. So this time when it gives us the tool calls, it actually shows that it has the list of random basic words in English ready, and it's going to pass those as an input into the translate words tool. So this time we don't seem to have had that mistake where it's created that placeholder list and passed that in instead. And then if we scroll down to the output of that tool call, we can see that we've gotten that translations dictionary just as we expected. So we have the first word that we saw above, apple, and that's translated correctly into manzana. And then if we head down to the bottom to the final output from the agent, we can see that we have that list of 30 words and their translations. So now we have a way for our agent to get word lists and translate them, but this is still not the most helpful thing for learning languages. It might actually be a bit more helpful if our agent can turn those words and translations into flashcards. And to do this, we're going to go beyond creating internal custom tools to exposing our agent to external tools through MCP. So what is MCP? Well, MCP stands for Model Context Protocol. And as you might have guessed from the name, it's a standardized protocol which makes communication between AI systems like agents and external tools much easier by standardizing those communications and breaking away from a reliance on custom connections. So these external tools are hosted on MCP servers. This is really just a fancy way of describing any local program, any background service, any remote API wrapper, which communicates with AI agents via MCP. As you can imagine, and as you'll soon see, there are an absolutely enormous number of MCP servers available, some free, some paid. And these will really help expand the range of functionality of your AI agent. And then because we're talking about external tools, I'm sure you can imagine that some of these carry security risks when used with agents. And this is something we're going to cover more in the next section. But for now, let's see how we can integrate some external tools via MCP in order to turn our words and their translations into flashcards automatically. So as you can imagine, with the current popularity of MCP servers, there are many, many different ones available. But one of my favorite sources is mcpservers.org. And you can see that this site has many servers, and these fall under all sorts of different purposes, things like web scraping, communication, productivity, development, the list goes on. But I'll leave you to go through that in your own time. For now, we are going to be using an MCP server called Clanky, which is going to allow us to create flashcards with a very popular piece of flashcard software called Anki. So both Clanky and Anki are free to use. And you can see that although Clanky says it's designed to be used with Claude, it can in fact be used with any LLM. So we can use it with our Qwen 3 model as well. So you can see that Clanky has quite a large number of tools that allow us to interact with Anki. It allows us to create and manage Anki decks, create basic flashcards, create close cards, update existing cards, add and manage tags, view deck contents and card informations, and it integrates with a plugin for Anki called Anki Connect, which we're going to be talking about in a second. So installing the Clanky MCP server is really simple. The first thing you need to do is just clone the repository in a place of your choice. If you don't already have npm installed, you will need to install that. And then from inside that Clanky directory, you build your MCP server locally by running npm run build. And inside that directory, you're going to end up with an index.js object. This is what you're going to need in order to connect to the MCP server inside our agent. And if you have any issues, you need to do some debugging, head over to the Clanky page on mcpservers.org that has the full set of instructions, and I'm going to be linking that in the resources. The next thing we need to create Anki flashcards is, of course, the Anki application. So as I mentioned earlier, this is a free desktop application. You can download it by going to apps.ankiweb.net, and you just follow the instructions to download it. So the final piece of setup we need to do is we need to add the Anki Connect plugin to Anki. And if you go to the website, I'm going to have that linked in the resources. You can follow the instructions to do that. And Anki Connect is basically going to allow our agent to communicate with Anki. Now, with all the background setup done, we're now ready to start integrating our Clanky MCP server into our agent. And the first thing we need to do is to find the path to that index.js object that we built. This is our MCP server. So basically, this is going to be inside your Clanky folder in the build directory. So have a look for it there. And you can see I've just defined it as a new variable in the main.py script as clanky_js. And you can also see that we've imported a new method, and that's the multi-server MCP client method from LangChain MCP adapters. So the next thing we're going to do is to go down to this setup tools function, and on top of the local tools that it's already using, we're going to add those MCP tools. So we create this client, which is an instance of the multi-server MCP client method. And you can see within that, you have the option of adding multiple MCP servers, but we're just going to add the Clanky one. And you can see from the arguments that we're adding, what we're doing is registering and connecting to that external node-based MCP server, the Clanky server, via standard I/O. And then we need to bind these tools, the tools available via Clanky, to the model. So we do this using this getTools method on the client that we just created. And then we're going to add these bound tools to what's returned from this setup tools function. And what this getTools method does is returns to the LLM a list of tool specifications for the MCP tools, things like the names, the description, the JSON schemas for arguments. And this is the stuff that we've been explicitly giving to the model when we created our custom tools. And then there's actually not that much left to do. Really, the last thing that we need to do in terms of changing the code for our agent is to update the example workflows that we provided in the system prompt. Now, because our workflows are considerably more complex now, we've now added several more tools and they need to be called in a certain order. It's best to be very explicit in these examples. So I've just pasted 2 examples that I prepared earlier here. So in this first example, we are prompting the agent to get 20 easy words in Spanish, translate them to English, and create a new Anki deck with them called Spanish Easy. So you can see, in addition to all of the usual fields that we've been covering, we also have this new tools workflow that we're giving to the model. And basically what we're telling the model is we need you to execute these things in a specific order. Get n random words by difficulty level first, then translate the words, then use the MCP tool create deck, then use the MCP tool create card. So a similar thing with this second example. Get 10 random words in German and create a new Anki deck with them called German words. So in our workflow, we specify that we first need the model to call get n random words, then MCP tools create deck, and then MCP tools create card. So you can see that we're attempting to add this additional structure to teach the model what it's supposed to do. And then the last thing we need to do before we can run our agent is to open the Anki desktop app. So I'm just going to open up Spotlight Search, type in Anki, and then open up the app. So we just need to have that running in the background while we run our agent. Okay, so let's now go down and update our user prompt. So we are going to change the source language to German. We're going to change the target language to English. So now we have please get 10 basic words in German, translate them to English. And now we're going to add this additional instruction and add them to an Anki deck called German Easy. And then we're just going to go ahead and run the agent. And because we're asking the agent to do significantly more than we were previously, this is going to take quite a bit longer. So I'm just going to fast forward through and get us to the point where we start seeing output. And then, of course, because this workflow is a lot more complex, there's a lot more output here. So let's just scroll up to the top to see what it did. So first, it's determined the source language, which is German. The number of words is 10. The difficulty level maps to beginner. And it has decided that the first step is to correctly call that get n random words by difficulty level tool. And then it determines that the next step correctly is to translate the words to English using the translate words function. And then it doesn't actually say anything about using the clunky tools. But if we go down to the tool calls, we can see that indeed the first tool call is to get n random words by difficulty level. And then the next is to translate words. And then if we keep going down, we can see that it's created the deck, which is the correct next step. And then it's just creating individual cards in different tool calls for each of these tools. And then, of course, the final step is to go over to Anki and check that it did what it said it did. So if we open up the Anki app, we can see that indeed there is a deck called German there. And when we expand on it, we can see that specific easy deck that we asked for. And indeed, as we requested, this contains 10 words. And then if we open up this deck and we have a look at the words by clicking Study Now, we can see these are the exact words and translations we saw during the running of the agent in the debugger. So we have Auto and its translation car, we have Sonne and we have its translation sun, and so on and so forth. So it's been pretty cool to see our agent grow from a simple little program that could really just extract random words to something that can communicate with an external application and automatically create translated flashcards. So to wrap up, I just want to very briefly discuss some considerations about security when it comes to building AI agents. Because these pieces of software rely on LLMs to do their processing and they're non-deterministic, they actually have some unique security risks that other pieces of software don't. We're going to talk about those in this section. So to explain these security risks, I'm going to be referring to this really great article from Corny Sietsma. And of course, I'm going to link to this article in the resources. I'm just going to touch on his main points, but I really recommend you read this all the way through before you try building your own agent. So one of the key points he makes is that LLMs, as we've already discussed, work by ingesting text and trying to predict the best next tokens. So this means that essentially they're treating everything as part of the same gigantic text blob. And this means attackers can sneak instructions into places you'd never expect. A document, a web page, even something as seemingly innocuous as a bug report. If the model doesn't realize these instructions are malicious, it might just simply follow them. And that's basically what a prompt injection attack is, tricking the model into acting on commands hidden inside the data that it's supposed to analyze. And the really problematic thing is that even reasoning models have a poor ability to distinguish between genuine and helpful instructions, making them very vulnerable to prompt injection attacks. So this gets especially risky when an agent hits what Simon Willison calls the lethal trifecta. It has access to sensitive data, it's exposed to untrusted content such as that on the open internet, and it can send information back out into the world. When these three things overlap, even a small embedded instruction can turn into a really big security problem. Imagine you have an agent that can read internal files or credentials, it can pull in content from public sources, and then email results to someone. In this setup, all it takes is one prompt injection to make the agent leak secrets or perform actions it was never supposed to. And it'll do it without asking for permission, because as far as it's concerned, it's just following instructions. We saw that with our own agent. So that's why we can't treat prompt injection attacks like they're rare edge cases. Anytime you give an agent autonomy, access to external inputs, and a way to communicate outward, you've created a potential security hole. But there are ways to reduce the risk. You can break up your system privileges so that no single agent has all three of these lethal capabilities in a multi-agent setup. You can sandbox your agents so their access is limited, and you can split tasks so that sensitive data and untrusted content are never mixing in the same step. So again, I've really just touched the highlights of this article, and I really recommend that you go away and read it before you start designing your own agent. It is an absolute goldmine of information, and it can really help you to mitigate any risks that your agent might have. So that brings us to the end of our tutorial. Thank you so much for completing it with me, and I hope you've enjoyed it. So looking back at this tutorial, we have covered a lot of ground. We've established the basic building blocks of agents and specifically how to build one in LangGraph. We've looked at how to specifically create a React agent and how to give it access to a variety of tools, both internal tools that we custom write ourselves and also external tools via the MCP. We had a look at important theory underlying both agents and reasoning models. And we also looked at why reasoning models might not always be the best fit for a particular task. And we also covered important basic techniques in text cleaning and processing and some classic natural language processing techniques. And of course, this is just the beginning for this project. There are so many more things we could do with this language learning agent, and I'm sure you had a lot of your own ideas while you were watching this tutorial. So I had a few ideas of my own while I was making the project. And one of the first things that I would do is go back and revisit those word lists that we sourced for all of the language data. We could see that some of them didn't quite look right, maybe they were incomplete, so we might want to find higher quality data for some of those languages. We might want to add more tags or descriptions to the words. So we already added the word difficulty, but we could potentially add something like the part of speech, things like nouns, verbs, adjectives. This is very useful for language learners. We could actually add a long-term memory component to keep track of the words that have already been written to flashcards so we don't have repeats. And we could add tools to create more advanced types of flashcards. So for example, Anki and actually the LangChain MCP server allows you to create types of cards called close cards, where you learn a word by seeing it in a sentence. So we could create another tool that allows us to create close cards. And naturally, you don't need to build a language learning agent after this. With the tools and techniques that we've covered in this tutorial, you can go away and build whatever agent you can dream up. So just before we wrap up, I'd like to remind you about a few things I mentioned throughout this video. So if you want to keep in touch, you want to reach out to me, I've included my social media links in the description of this video. And I've also included a number of other content I've created related to this video that you might find interesting. And then finally, if you like the video, please do give it a like and subscribe to the channel. It really helps us a lot. So thank you so much for joining me again. I hope you had fun, I hope you're feeling confident, and I hope you're feeling inspired to go away and build your own agents project. And keep in touch. I would really love to see what you build for yourself.